Hello, everybody. Welcome, welcome. Welcome to day 3. We'll just wait for everybody to be let in from the waiting room. Hope you've been enjoying the conference so far. Okay, I think we can admit a few more people. And our lock, Yolene, is helping us admit everybody. Okay, so I think we're almost getting to everybody in. Oh, people are still joining a little bit. Okay, I'll just start a bit with some housekeeping rules. So welcome back to day 3. We really hope you've been having a good conference so far. For this session, we're going to be talking mainly about AGB stars and molecules in AGB stars, as well as a radiative transfer tool to actually model them, the investigations that we have, and also looking at the dust and gas content of galaxies. So I think it's going to be a really cool and interesting session. Some rules for while we do this and let people in. For the audience, please make sure to mute yourself and turn off your camera during the presentations. So just keep those off. If you'd like to ask a question after someone's talk, then you can raise your hand. And the way you do that is with the reactions button at the bottom of your Zoom, in the Zoom tools. And then you can also, so you can have the option of raising your hand, or if you'd like, you can put a question in the chat and I can call on you and I can read it if you'd like, or you can ask it yourself and you can unmute and turn on your camera. It's up to you. So that's for the audience. For the speakers, we have an invited speaker today. The invited talks are 20 minutes presentation and 5 minutes for questions. And the contributed talks are 15 minutes of presentation and 5 minutes for questions. And I'll give you a 2-minute warning before the 20 minutes is up for Pablo, and for the rest of the speakers, I'll give you 2-minute warning before the 15 minutes is up. Just to make a note for everybody that we're recording this, and this is to make sure that we can have the videos on our YouTube channel, but we're recording. And I think that we can just wait a little bit longer to admit everyone. With the Zoom links, people will be moving in and out, so I'll be quite strict with time, and I'll try to stick to the schedule just in case people are joining and moving between talks and other things that you do while you're on Zoom. And let's see, is there anything else that I need to say? I think that's about it. Okay, so we'll begin with our first speaker. We have an invited talk from Pablo Fonfria. He's based at Physique in Madrid in Spain, and he'll be giving us a talk on an infrared view of the molecular content of AGB stars. Pablo, I'll give you a 2-minute warning before the 20 minutes, just a verbal warning. I'll just say 2 minutes, and then you can wrap up. I'll spotlight you actually as well. Would you like to share your screen? Make sure it's all working.
Okay.
Good, yes, that's looking good. And I think that I'll just start my timer. We have just 1 minute. If we just wait 1 minute, just to keep to the schedule.
Mm-hmm.
And I think that we can start now. So go ahead. Thank you so much, Pablo Fonfria, our first invited talk. Go ahead.
Thank you. Good morning to everyone, and thanks for attending this talk. First, I want to thank the organizers of this conference for inviting me to present our work, and to all my colleagues for their efforts in the development of our research. I'm going to start this talk with the pros and cons of infrared astronomy and some highlights of molecular detection in infrared range. Next, I will present the results of our last works, and finally, I will talk to you about our ongoing work. Infrared has been used to observe AGB stars since long ago with a high spectral resolution to explore the molecules emission and absorption of the most abundant species. The instruments currently available allow us to observe hundreds of gravitational lines, typically in less than 1 hour per setting. A bit of information about the physical and chemical conditions throughout the observed circumstellar envelopes is encoded in many lines at the same time, which gives us a complete point of view, even in the case there are observed lines that are useless for any reason. The continual emission of AGB stars produced by the central star and the dusty component of the envelope is absorbed by the molecules in front of it. In this sense, this absorption provides us also with high angular resolution information that can be in the near infrared as high as the stellar diameter. One of the greatest strengths of infrared observations is that molecules without a permanent dipole moment can be observed, something that is not possible in the millimeter range. Infrared observations are affected also by problems, of course. The most important one is the atmosphere that blocks a big fraction of the infrared range, making it impossible to observe certain molecules with ground-based telescopes. As it can be seen in this figure, the spectral range between, well, of course, this is the atmospheric transmission, and the spectral range between 1 and 100 microns is substantially blocked by the atmospheric opacity created mainly by water, vapor, and carbon dioxide. However, the rest of the range is available to ground-based telescopes such as the LTF or the VLTs. And the spectral ranges that are unavailable can be partially explored with Sofia, and that flies at an altitude of about 35,000 feet, or where the atmosphere is optically much thinner. They can be also completely explored with the space telescopes such as the ISO or the Spitzer in the past, or the JWST and Origins in the future, but only with a low spectral resolution. Unfortunately, space observatories are not launched very frequently, and we can observe with them only during a limited periods of time. Low spectral resolution observations imply resolving powers lower than a few thousands that are very useful to explore spectral energy distributions or solid state bands, as in the case of the figure to the right, where the presence of different materials can be inferred to be part of the dust grains. Many molecular bands can be detected as well, even though some of them are strongly overlapped, as you can see in the figure of the continuum of YCPN. In this spectrum, we can figure out that there is CO and C3 in the band that peaks at 5 microns, for instance, because the band profile shows a weak depression at the frequency that corresponds to the CO fundamental band. But this is not the case many times, and it's very difficult to know if a molecule is with a low abundance is in a band or not. One of the most interesting capabilities of low spectral resolution observations is detection of new molecules, as in the case of benzene that was detected in ppm CRL 616, or the fullerenes C60 and C70 that were detected in the young PN DC1. However, high spectral resolution observations can also reveal the existence of new molecules, as it occurred with C3 and C5, which were discovered in IRC 10216 long ago. The regressional bands are strongly blended with the CO fundamental band in the low spectral resolution observations that you can find in the figure to the left, where the CO band dominates the spectral range between 4 and 5 microns, hiding the bands of any other molecule. In the spectral range, in the high spectral resolution observations, the lines are isolated and can be more easily identified. A good example of finding the spectrum of a molecule in the spectral range with a high line density is the case of the acetylene in IRC 10216. The acetylene was expected to form in this star, but there was no trace of its band in the low spectral resolution observations taken with ISO. Nevertheless, it was possible to find it in the high spectral resolution observations carried out with the IRTF and the spectrograph Texas, even though it is in a spectral range with crowded with acetylene, CS, and SiO lines. The lines seems to of acetylene the acetylene seems to form in the intermediate envelope with an abundance that chemical models can replicate, as you can see in the figure to bottom left. Right. It is possible that the outer envelope of IRC 10216 is somewhat clumpy, and the galactic UV radiation field penetrates the envelope much deeper than expected. A few years ago, we started a new high spectral resolution project with Sofia and the spectrograph X's, aiming at comparing the molecular content of a sample of AGB stars with different chemistry and mass rates. Our goal was to observe this sample of stars at 7.5 and 13.5 microns to look for molecules such as acetylene, carbon dioxide, water, methane, and among others, to test the current accepted chemical models. Most of the survey is completed, and we have the first results yet. We found weak number emission lines in the spectrum of our LEO, around 13.5 microns, that turn out to be CO2 and 13 CO2 lines. This represents the first time that CO2 is detected with an observatory embedded in Earth's atmosphere, as far as we know, and it is also the first detection of CO2 in our LEO. You can see all the features in the spectrum, in the synthetic spectrum over here, and here in this panel, very clear here and here and here. We found between the telluric features about 250 lines of CO2 and 13 CO2, most of which are vibrationally excited. Most of the CO2 lines show Gaussian-like profiles, and their widths are about 5 kilometers per second once if the effects of the spectral resolution has been removed. These lines are probably formed very close to the sphere photosphere. However, some of the lines are better fit with two components, which suggests that they come from a region of the envelope that covers part of the gas acceleration zone also. We did a regressional diagram with the strongest lines, which you can find in this slide. Apparently, the CO2 excitation is dominated by the strong stellar emission with a lower, fainter contribution from dust. CO2 molecules can be excited up to vibrational states with energies of 6,000 to 7,000 Ks to the excite afterwards. The derived column density is compatible with previous measures of a few other rich stars, but when we were gathering all the information from the literature, we realized that there is a large dispersion in the estimated column densities that seems not to be related to mass rate. However, we are not sure if this dispersion has chemical origins or it is related to uncertainties of the lower spectral resolution observations or the modeling. This is why we are going to start a new project with Sofia and Nexis, which is already accepted, to compare the carbon dioxide and water bands of a sample of 30 or rich stars. Our last results based on the Sofia and Nexis data are those derived from a detailed analysis of HCN in the observations of the J-type star YCBN. We complemented these observations with IRTF, and the spectrograph Texas data are 13.5 microns and millimeter observations that were taken with the Iron 30-meter telescope. The HCN lines are strong and involve lower regulational levels with energies up to 4,000 Kelvin. But in this figure, you can see the data around 14 microns, along with the line identification and the best fits to the HCN lines. The spectrum contains also many lines of acetylene. These data were taken with the RTF and Texas, and shows a less crowded spectral resolution, and less crowded spectral range, but also with many lines of HCN and C2H2 lines. Sofia axis observations at 7.5 microns show another very crowded spectral range with lines only in absorption, as you can see in the figure to the right. In addition to the HCN lines, there are more lines of acetylene and a particularly high number of CS features, which involve lower rotational levels with energies up to 7,500 Kelvin. In the regressional diagram of HCN, we found that there are 4 different populations with temperatures that range between 100 and 3,500 Kelvin, and the average column density derived from this diagram is only 1 order of magnitude lower than that of IRC 10216, which I remind you that has a mass loss rate of about 200 times higher than YCBN. The HCN abundance of YCBN is of the order of 10 to the minus 4, which is somewhat high for a carbon-rich AGB star. This diagram reveals something else. The lines at 7.5 microns are not compatible with the lines at 13.8 microns. However, both spectra were taken with during the same nights and with the same instrument. And moreover, the spectra are normalized and they are not affected by possible uncertainties such as those related to flux calibration, because they are not flux calibrated, of course. Thus, we conclude that either the gas density distribution or the HCN abundance distribution are or can be asymmetric. There is still much information encoded in the observations carried out with Sofia and Nexus. This figure shows the observations of all the stars around 13.8 microns and the synthetic spectra of several molecules of interest. It is easy to see at first glance bands of certain molecules such as acetylene and hydrogen cyanide in the spectrum of IRC 10216, that is this one. And this is the acetylene band, this is the HCN band. These bands can also be found in the spectra of YCBN, as we saw before. And they also appear clearly in the spectrum of W Aquila, that is here. This is the band, is of course less strong. This is the band of C2H2, and this is the band of HCN. This band supports the conclusion by De Beck and Olofsson that recently showed the marked carbon-rich character of this S-type star. However, the CH2H2 band is not present in the other S-type star of our survey, which is Key Cygni, and the HCN band is much weaker than for W Aquila. The spectra at 7.5 microns show us also interesting features. The water lines are evident in emission in the spectrum of BX Sagittae. That is this spectrum here. These are the, this one, sorry. This is the band of water. And IK tau, that is this spectrum. You can see here the lines also at much significantly weaker. The spectrum of Leo shows a clear complex band that covers the whole observed spectrum, spectral range, and belongs to SO2. Nearly the same pattern can be observed, of course, the spectrum of Leo is this one, and nearly the same pattern can be seen in the spectrum of Key Cygni, that is this one. You can see this high number of small peaks that is actually a band. However, you can also find this same pattern in the spectrum of IK tau, that is here, but less stronger. And but it is not possible to find the CO2 line pattern in the spectrum of BX Sagittae, that is here. Maybe it's there, but it's much weaker, so it's not noticeable at first glance. And no trace of SO2 has been found in the spectrum of W Aquila, that I will remind you that is here. It's mostly flat, actually, and there is no so complex spectrum. Sorry. This supports that the fact that the W Aquila and Key Cygni have a different chemistry, regardless of the fact that both are S-type stars. This difference could be due to a different evolutionary state, actually. This table summarizes our current progress concerning detection of molecular spectra. There are molecules in this table whose spectra has been searched for, but we still cannot be sure, cannot be decide if they are in the observations or not. The data are complex with many molecular lines, and there are some steps to check before being sure that the line pattern is present or not. So we hope to make significant progress during the next months. And to finish this presentation, I want to introduce another project related to AGV stars. This time, we aim at looking directly at stellar photospheres, and we perform a survey of AGV stars and red supergiant stars with the Calar Alto Observatory and the Carmenes spectrograph in the near-infrared and visible ranges. All the data are already taken and reduced, and we are analyzing the observations right now. We have focused on carbon-rich stars to start with this. Most of the lines that we have found are of C2 and CN, something that's already known. But the lines of these molecules display two different components in stars with medium to high mass loss rates. One narrow and another one much broader. In low mass loss rate stars, the narrow component is absent completely. A narrow component, when present, peaks at the last terminal velocity. However, the broad component is shifted in IRC 10216 and AFGL2233 at positive velocities. The shifts of the rest of the stars are negligible, and these components can be assumed to peak as the systemic velocity. The comparison of the spectra reveals that the opacity of C2 and CN lines increases as the mass loss rate decreases, which we interpret as a higher abundance of carbon in gas phase for low mass loss rate stars. This slightly indicates a higher dust formation efficiency for high mass loss rate stars, probably related to a higher gas density that may favor the condensation rate of refractory molecules and atoms. The analysis of the fundamental band and several other tones of the Phillips system of C2 in the spectrum of IRC 10216 suggests that the narrow components of the lines are formed in the outer envelope, as it is already known. However, there are another population with a slightly higher temperature of 70 Kelvin. The cold population is usually associated to the shell where the acetylene and hydrogen cyanide are dissociated, which is placed roughly at 15 arcseconds. But the warming population shifts inwards the formation of C2 down to 5 arcseconds from the star.
2 minutes.
Okay, I'm about to finish. Finally, the Rubironic diagram for the lines observed in the spectrum of IRC 10216 that corresponds to the broad components is shown in these figures. The data dispersion is high, but the rotational temperature and the column density can be reasonably well determined. The temperature is compatible with the effective temperature of the star, so that this component can be placed at to be formed at the photosphere. We tentatively propose two scenarios to explain the width of the lines out there and expected Doppler shift that is of 15 kilometers per second for IRC 216. The first one is that the C2 is in front of the star is falling on the photosphere, of course. The second one is a bit more complex to explain, and it could be that we are observing is it's produced by the stellar photosphere, the stellar radiation that is absorbed by the photospheric C2 is reflected in the dust grains that are behind the star and are moving away from us. It's as I told you, it's not very easy to explain, but it's I think it's easy to understand actually. Let's finish now. As a brief summary of this talk, I will say that infrared observations are very useful to study molecules with no permanent dipole moment, and they are complementary to millimeter observations to study molecules with a permanent dipole moment. Low spectral resolution observations in the infrared provide us with very sensitive data, but the molecular bands of the most abundant molecules frequently hide bands of lower abundance molecules. A combination of both kinds of observations is very fruitful to describe the molecular content of a given star, of course. With high spectral resolution observations, we can get hundreds of reversional lines simultaneously, which allow us to derive sound results about the physical and chemical conditions in the circumstellar envelope. So I will stop. I'm really so sorry, I forgot to pass the slide. So I will stop here, and thank you for your attention, and I will take any questions you will have.
Fantastic. Thank you so much, Pablo. Are there questions for Pablo? I see one here already from Stefan Utenthaler. Go ahead, Stefan. He can't raise his hand, so he sent a message.
Yeah. Hello.
Hello.
Pablo, thank you for the talk. I am interested in the water lines that you detected. So did I understand correctly that they are in emission, and did you do any further analysis yet?
Yeah, not yet. I have more knowledge about that. Of course, I revised the data much closer, but and I can tell you that I talked about the mission because it's the most obvious in this figure. Because if I try to show you all the observations, I could take I don't know, half an hour. So there's no time for that. Okay. But of course, this emission is come with absorption as well. But part of the absorption is overlapped with the telluric features. So the emission is clear there because the Doppler shift of the observations are favorable to see the emission part, but there is a component, an absorption component as well. I can't tell you anything else about the analysis because I didn't do it yet.
Okay. Good. Okay.
Oh, I have talked to
you. Yeah, you can carry on in Slack. If we have time, you can even ask it after Sofia. I see your hand raised. Go ahead.
Yes, thank you. Thank you for this super interesting talk and for doing this work, which is very difficult and takes a lot of time. So I was wondering, did you consider observing any of the stars at several epochs? And if so, did you see any variations in the lines?
Yes, I did consider it, but it's a bit difficult because of the observing conditions, actually. It's, axis is not always available. So there are different times during the year that the axis is mounted on Sofia, and you can use them. So it's difficult to select a specific time to observe the different stars, but it can be tried to be done, of course. It will be very interesting to observe a given star. I'm not sure if many of them, but maybe 2 or 3 or stars, and monitoring the emission during maybe 2 years. So I think it's something that it can be done, and we can try to do it in the future. If you want, even if you want to do it, I can help you. If you don't want to do it, probably we will do it any time in the future.
Yeah, thank you very much.
You're welcome.
Great. Any other questions? We have time maybe for one more. Stefan, do you want to go ahead with a quick one?
Me? No, I just wanted to mention that I have cryospectra of red giants, slightly less evolved, and I also found water emission there. So maybe we can compare some point, or would be interesting if you can keep me up to date with your progress.
Okay, great. Thanks very much. And I have a very quick one. What can we expect from JWST? Will we be able to do time dependent, as Sofia was suggesting? And what can we expect to come?
Can you repeat, please? I lost the.
What can we expect from JWST?
Well, it's difficult to say, but probably the JWST is very interesting space observatory, but it's a bit tricky to use it because it's so sensitive that if you look at close stars, you can burn the detector. So it's you have to. It's really sensitive. So you have to use the JWST to observe stars that are far from here. In this sense, it could be very, very interesting to compare the AGB stars or EvoLved stars in general in other galaxies with the stars in our galaxy, of course, because I'm not sure exactly if we can get much information from close stars to us, but we can try to compare different chemical evolution. If there is a different chemical evolution of different formation in other galaxies. This is, I think, this is the most important thing we can get from the JWST. Of course, other people could have other ideas and have a project that I don't think on, and it could be very interesting. So let's see what happens.
Yeah, it sounds like it will be really exciting. Let's continue to chat about that and other questions you have for Pablo. Thank you very much for the talk, and we can carry on chatting in Slack. Next, we have a contributor talk from our chair for this meeting, Taïssa Danilovich, who's at KU Leuven. Taïssa, are you there?
Yes, I am.
If you could share your screen.
Yes. There we go. Is that okay?
Yes, I can see that. And Taïssa will tell us about halide molecules around the S-type AGB star W Aquila. Go ahead, Taïssa.
Okay, thanks, Shazreen. W Aquila is an S-type AGB star, as was in my title. So this was mentioned in the previous talk, but just to quickly recap, S-type AGB stars are intermediate chemistry, somewhere between oxygen-rich stars and carbon-rich stars. So the thinking is they're on their way to becoming carbon-rich, but aren't there yet. So the carbon to oxygen ratio is close to 1. W Aquila in particular is a good S-type AGB star to observe for a few reasons. It's relatively close. It has a moderately high mass loss rate, which makes, combined with the distance, a lot of molecular lines much easier to detect just because they're brighter. It's also in the southern sky, so we can observe it with ALMA, which is what I'll be showing you shortly. And although it has a binary companion, it's thought to be relatively distant. So this doesn't really make any particularly strange problems for us in the inner circumstellar envelope, though it does also create a bit of a spiral in the CO that we can see in the CO. So W Aquila has already been studied quite a lot, so we know a lot about it. A lot of molecules have already been detected, but today I'll be presenting new detections of aluminium halide molecules. So that's AlCl and AlF, that's aluminium chloride and aluminium fluoride, which we've detected in an S-type AGB star for the first time using ALMA. So one reason these molecules are interesting is because of the aluminium content. So aluminium is thought to be involved in the dust formation process. So studying what it's doing is interesting from that point of view. Then on the topic of the actual halides themselves. So the halides are the column in the periodic table that's second from the right. So fluorine, and here aluminium fluorine, but fluorine itself is particularly interesting since it is formed in AGB stars while they're on the AGB. The exact amount overall that's formed is still a bit under debate, but it's thought that maybe about half of the galactic fluorine has come from AGB stars. So while it's synthesized inside the AGB star and then dredged up to the surface, this could give us an indicator of age. So more fluorine, just like more carbon, means that the AGB star has had more third dredge-up events. That could give us some indication of age as well. And then chlorine is not formed in AGB stars, but has been found to be a reasonable indicator of metallicity just in the galaxy in general, in stars generally speaking. Now, the data that I'm talking about here is from the Atomium Large program. So this is an ALMA Large program where I've given a bit of an overview spectrum here. We observed several windows from the 214 to 270 gigahertz range. You can see there's a few gaps there, but a lot of coverage. So this represents the highest spatial resolution observations of W Equulae that are available to date. And in total, we observed 106 lines of all sorts of molecules, of which some were ALCL and ALF. So now, because of the resolution and the largest angular scale requirements of the Atomium project, we actually obtained data for W Equulae from 3 different ALMA configurations. So there's the extended array, which gave us the highest resolution observations, then what we call the mid-sized and the compact array, which are just different configurations. So here I'll mainly be talking about the extended array and the combined data. So that's combined is when we combine all of the observations into one cube. So starting with aluminium chloride, down the bottom here, I've shown channel maps. I'm not sure how visible it necessarily is on your screen, but the star is the location of the star is approximately represented by the red contours in the center. Those are actually the 50% contours of the continuum. And as you can see here, we've got what looks like a bit of clumpiness in the ALCL, and some of this is partly probably noise. But when we add all the channels together to get the moment zero map, so that's basically summing all the channels together as I've shown up here, we see there is a bit of a bias. So slightly more ALCL is seen to the south and east of the star, but overall it's almost centered on the star. Yeah, and this is at the highest spatial resolution that we have available. Aluminium fluoride turned out to be a bit more of a sort of problem, observationally speaking. While we had a bright region in the center, so sorry, in this plot, I should say the colors and the dashed white contours represent aluminium fluoride. So we see quite a clear detection in the center, but then when we sum the channels for the 0th moment map, we see this more diffuse, also clumpy, perhaps a bit noisy emission, but it's off center even more dramatically than we saw for the ALCL. So the emission is biased mainly to the north for no clear reason. I mean, we don't really understand why this happens. But as you can see, the ALF is a lot more spatially spread out than the ALCL, which is represented by these black contours. So these look slightly different to the previous slide because here I've just plotted the ALCL at a slightly lower resolution. It's the combined observations, and the lower resolution is just to make it a bit easier to see on this graph, on this plot, without having sort of the noisy edges of the line. And the position of the star is represented by the red star in this plot. So you can see that while the brightest portion of the ALF and ALCL is not far from the star, further out there is a bit of a bias. So this off-center aspect of both of these molecules suggests that, well, it'll be a little bit difficult to approximate with spherical symmetry. However, especially for ALF, this diffuse, slightly clumpy emission is also very difficult to try and approximate in 3 dimensions. So what we do is we do, in fact, model this with a 1D radiative transfer model. So we actually just take an azimuthal average of the data to obtain the spatial information. So this, of course, as we've just seen, will not be a perfect model, but does give us a reasonable approximation of the abundance of these 2 molecules, and especially the abundance closer to the star, where for ALF, that was more central, and for ALCL, that was more noisy and clumpy. Those clumps in ALCL would also be fairly difficult to model in 3D. The other argument in favor of the 1D modeling is that we do actually need to include a large number of levels and vibrational levels, so rotational and vibrational levels, since the term energies of the vibrational states are such that they're very susceptible to infrared pumping. So from radiation from the star, the vibrationally excited levels contribute fairly significantly to the overall radial transfer balance of these two molecules. So we also, in terms of the 3D structure or lack thereof, on the left here, I've shown CO from our lowest resolution, which shows all the large scale structure. There's a little bit of resolved out flux here, but you can see some structure of sort of spiral arms or something like that in the CO. And the ALCL is very much confined to the center and not at all comparable to the extent of the CO. On the right, I've shown sort of a zoom in. The CO there is from combined observations, and you can see while there is a little bit of structure there, it is not very significant, and there's not huge density contrasts that we see. And the ALCL is, as you can see, found in the center where we can reasonably approximate this in 1D. So, forming our radiative transfer models, we looked at spectral lines extracted from the ALMA data. So we actually do see up to the V=2 vibrationally excited lines, rotational transitions in the second vibrational excited state, I should say. We don't detect the V=3 lines, but I just included them for an upper limit to make sure that the model was behaving okay. And when we take an azimuthally averaged radial profile, and also fit our model to that, we can get a pretty good fit from the data. So this, what I'm showing now, is the AL35CL results. So that's the main isotopologue of ALCL. And we also have AL37CL, where we don't detect as many lines. And we have a bit more noise in the radial profile because it's just overall a weaker line. And then finally, there is the ALF. So here we don't detect any vibrationally excited lines with any certainty. So we really just have that ground state 7 to 6 line, which I showed earlier, and the azimuthal average profile. The main discrepancy there really is in this region where the model doesn't quite match the observations, and that's exactly where the main offset in the emission is. So that's where there was more emission to the north and the south. That's in approximately this region. But we can fit the spectral lines reasonably well. So those are the plots of the results, and numerically, this is what we find. So as you could tell from just the ALMA observations, the ALCL is indeed quite confined, close to the star, and the ALF is a bit more spread out. We find a step function in abundance for both, different step functions. Yeah, and this will all be published in a paper that is close to submission, so hopefully coming to an astrophysics journal near you soon. So what is really interesting about these results is that we see the ALCL is destroyed close to the star. We don't quite know exactly what is causing this. It's possible that it is being incorporated into dust or just being destroyed through other chemical reactions. ALF persists further out, and this is actually less of a surprise since the bond strength of ALF is a bit higher than for ALCL. We also see a higher abundance of ALF in W Aquilae than is seen in the sun. This is, well, initially a bit unusual, but when you consider what I said earlier in the talk, that fluorine is produced in AGB stars and dredged up to the surface, this just indicates that there have been several or some dredge up events in W Aquilae, which we already know since it is an S-type star. The other interesting result, which is more an absence of results, is that actually chemical models predict that we should detect a lot more ALO and ALOH than we see. We actually don't detect it at all, even though both of these molecules are covered in the atomium survey. And the upper limits I found for both of these are quite low. So you might think, well, it's an S-type star. We see some carbony chemistry, as we saw in the previous talk. Is it just that there's not much oxygen? But both ALO and ALOH are formed from reactions with water, and we do see water towards W Aquilae with a high enough abundance that this shouldn't be a problem. So this is also a bit surprising, since it's thought that ALCL and ALF are formed from reactions with ALO and ALOH with the hydrogen halides HF and HCl. So chemically speaking, this remains a little bit surprising. So this is what we have seen so far, and what we want to look at in the future is we do have more ALCL and ALF detections in the oxygen-rich samples, the oxygen-rich sources in this Atomian sample. For some of these, we also have detections of ALO, so that would help understand the chemical interactions between all of these three molecules. So that would allow for a further investigation of halide chemistry and aluminium chemistry. So it would also be interesting to observe HCl, which is possible to observe the 1-to-0 transition with ALMA and some of the other transitions with Sofia. We'd also really love to be able to observe HF, though at the moment that doesn't seem possible, since it falls just outside of the windows that Sofia can cover. But if someone in the audience knows different, please tell me, because I would really like to observe that. So thank you. That is my talk. Any questions?
Thanks so much, Taïssa. Thanks. That's great. Questions? Perfectly timed, and it was so interesting. I even forgot to give you your 2-minute warning, but it was perfect timing. Questions for Taïssa? You can raise your hand, or I see Sofia. Go ahead, please.
Thank you. And thank you, Taïssa, for this interesting talk on our common favorite, W Aquilae. I was wondering, so you said in the beginning of your talk, you mentioned that you could use fluorine as an age indicator.
Yeah.
Are there any other observations that you can compare with, and to say anything about whether, because in the previous talk we heard that W Aquilae seems to be like more toward the carbon star range when it comes to other abundances of other molecules and so on. So I was wondering if there is any indication where you could say whether the fluorine gives you a hint if it's old, like if it's older than other S-type stars, or if it's more like the carbon stars or more like the M-type stars. You compare to the sun, which I guess would be an M-type star abundance, but
yeah, so ALF, has not been studied for very many sources. It's been seen in ISE 10-16 as most things, but the abundance and distribution there is very different. So ALF by itself is probably not a good indicator of the total F content for that star. HF has been detected for that star as well, but I think together they still add up to a little bit less fluorine than we're seeing in W Aquilae. So if for whatever chemical reasons that we haven't quite fully worked out, if most of the fluorine for this star for W Aquilae is in ALF, then that makes it a good indicator. Yeah, so that it is possible to find some unresolved detections of HF in PAX observations. We had a look for W Aquilae, and there's no conclusive detections, maybe one tentative one. And these were a bit clearer for, for CW Leo, it was also observed with Hi-Fi, but not covered for W Aquilae. That's another molecule to consider. And like atmospheric studies tend to assume that all the fluorine is in HF. So that is probably a big missing piece overall. And as for how we can compare it to other stars, just using fluorine, it's unclear until we finish analyzing the oxygen-rich stars. But it is true that we see more carbon-bearing molecules in Atomian as well for W Aquilae. So it does seem to be heading in the carbon-rich direction.
Cool, thanks.
Great. Any other questions for Taïssa? If not, thank you so much, Taïssa, and we can continue the discussion on Slack. We can ask some more questions there. Sorry, apologies for the noise outside. They've decided to cut the grass. And if our next speaker, Manali Jeste, could share her screen.
Yeah.
Good. So next we have Manali, who's at the MPIFR in Bonn, in Germany, and she'll be telling us about hot HCN in carbon-rich AGB stars. I'll give you a 2-minute warning before your 15 minutes is up. Thanks. Go ahead, Manali.
So yes, so as she said, I'm giving a talk on hot HCN and carbon-rich AGB stars. So we are here at MPI. We are collaborating with Carl Menton, Hyun Gong, and Katat Wong. So to give a brief introduction again of carbon-rich stars. So these are the stars, the type of AGB stars with surface abundance ratio of carbon to oxygen greater than 1, and if it's less than 1, it's oxygen stars. So these stars are going through various physical phenomena and they're ejecting material out in the atmosphere. And that's why we have a lot of gas and dust pushed out in the atmosphere, forming the circumstellar envelope. And this envelope is quite rich in molecular species. More than 90 of these species have been detected until now. And HCN is actually one of the most abundant molecule, the third most abundant molecule after molecular hydrogen and CO. So this molecule goes through, has 3 vibrational modes, and its vibrationally excited lines are quite interesting because they're easier to excite compared to vibrational CO. And that's why we can actually detect them from ground-based telescopes. So on the right, you can see a schematic diagram of such an envelope. So in the center, we have the star, and then there is a zone of parent species, and then followed by a dust formation zone. And then we have the area where the daughter species are born from the parent species. And then this material is then getting mixed with the ISM. So as you can see, HCN is present quite close to the star. And it's formed, that's why it's formed close to the star, and it can help to trace the innermost part of this envelope, which is actually what we confirm from our observations here. And it will further give us the information about physical and chemical conditions in this region. So to start with, we have collected 16 carbon-rich stars for our project here. And we have the criteria of that they are observable with apex, so in the southern hemisphere, and there have been previous measurements of these envelopes in the past. So on the right, you can see the sample of our AGB stars, so the 16 of these carbon stars, and we have taken them from Menton et al. 2018, and then Rao 2017, and Masalki 2018. So these stars actually have various property variations. So you can see that the mass loss rate varies from as high as 10⁻⁴ to as low as 10⁻⁸. And the period also varies from 200 days to up to 700 days. So this helps us to get information of different properties across various carbon-rich environments. So to start with, we did observations with apex 12-meter sub-millimeter telescope, and we conducted observations for more than 100 hours in wobbler mode and reduced the data with GILDAS and fit our emission lines with Gaussian fits for the vibrationally excited lines. But the ground state lines, which give more parabolic shape, we use the shell fit subroutine to fit these lines and get more constraints on the physical parameters. So what we did for detection is we put a detection threshold of 3 sigma, and that gave us the ground state detection of all the 16 sources. So V is equal to 0. And surprisingly, we also detected 29 HCN maser lines from 13 of our 16 sources. So as an example here, we have a W Orion, and on the left, you can see is the ground state line, and on the right is the HCN masers, the V2 equals to 1 line. So you can see that how much it's much brighter than the ground state line. So this is what we see in many of our sources. What other thing that we saw is like also expansion velocity of these stars. So here is a histogram that we plotted. So this is all the ground state lines for all of our sources in 322 transitions. And the median value of the expansion velocity that we get is about 16.1 kilometer per second, which is here in purple. And the other lines, so this is from the literature. These markings are from Ramstedt 2009. So this blue is the M-type star expansion velocity of M-type stars, green is of the S-type star, and red is of C-type stars. So you can see that our sample has more expansion velocity here, which could be because the targets of ours, of the targets that we are using, have higher mass loss rate. So to get more into understanding of these vibrationally excited lines, we can discuss a bit about the thermal emission of the HCN. So we detected actually 33 thermal lines towards 7 of our sources. So these lines have a quite narrow line width, and they don't reach the terminal velocity. And as an example, here is the IRC 10 to 16 to 1 transition with V2 equals to 3 vibrationally excited line. And these are the narrowest that we saw with an expansion velocity of as low as 5 kilometer per second. So since they're not expanding as fast, we think that these are arising from very close to the star, that is up to 10 stellar radius away from the star. What we also see are many major emissions. So these are the lines which are characterized by unexpected high intensity peaks, and also they have quite a symmetrical profile. So in Menton 2018, we have seen that the HCN masers are quite widespread in carbon-rich stars, and that is what we also see in our study here. We detected 24 new maser lines, and they were all newly discovered. And from our 16 sources, eight sources did not have any HCN masers detected until now. So we actually doubled the number of known HCN masers towards carbon-rich stars with our study here. And since these lines are quite narrow, they're quite useful to trace this wind acceleration region of the envelopes of these stars. But we don't know exactly the origin. But Menton et al. Just said that it is they could be pumped by the infrared radiation taking place around the star. To give you an example of the spectra, here is one of our beloved IRC 10 to 16 with 2 to 1 transition and in various vibrational modes. So we have the main beam temperature and velocity, and here is the ground state line. And then we have the vibrationally excited lines, all ranging from 2000 Kelvin to up to 4700 Kelvin. And you can see that they all have different shapes, but interestingly, you can see that the V2 equals to 1 line, both have a similar energy, upper level energy, but they have a very different intensity. So this is quite low compared to this one, which is quite bright, quite intense. But this line is not, it's a maser line, so it's not as intense as it used to be. So what we did is we tried to look for a time variability that is taking place in HCN masers. So we, with our limited availability, we have here we found 3 epochs of these lines. So the first one in blue, as you can see, is from Lucas and Sernicharo. The observations are taken in 1989. And then the red ones are from Menton et al. 2018. The observations were taken in 2015. And the black one is from our study, taken in 2018. So you can see that the lines are going through a dramatic change, not just in ground state, but also in the maser line. So it not only changes the velocity peak, but also the shape of the line. And this is seen actually in 3 of our sources, for which we have actually the data to compare with, to look through across different epochs. And we also see a change in one F line. So this is another example of II loop that we see here, that you can see that the change, there is also variability seen in the maser line, but also it has increased the flux density by, I think, more than 20%. So we don't know, I mean, what is the reason, because there are not enough epochs to trace this. But I mean, it could be from the shocks by pulsations, or also because inhomogeneity caused by the outflowing wind. But if we could monitor it more often probably we can trace the reason for these variability in these HCN measures. So to understand more about this vibrationally excited lines, we also made a population diagram for IRC 10 to 16 and CRL 3068. So this is again upper level energy and the NU by GU. Since we have a number of more vibrationally excited lines detected towards IRC 10 to 16, we have more data points and we could get a better constraint. So here the triangles are just for representation of measures included for which show the non-LTE distribution in both of these cases. So what we get is the excitation temperature of more than 500 for IRC 10 to 16 and more than 600 for CRL 3068, which is actually more than what is in the literature by Sernicharo 2011 and Nicholas 2018. And this could be because of the reason that these lines are actually arising from hotter parts of the envelope, and they are tracing the more in the most part of the envelope, and that is why we are getting more higher excitation temperature. So that is what we have been doing for our single dish data, but in the future we would also like to analyze the existing ALMA data that will be provided by a collaborator, and it could help to resolve the atmosphere and get information on the dust formation zone of this envelope. So as an example, here is an RFGL 4211 for HCN 120 line, and you can see the extent of the envelope is about 10 arcsecond, and it's not very spherically symmetric envelope. So this kind of information is what we would get from interferometric data. And along with this, we could be able to get, able to model this data and get information of the source structure, abundance, etc. And these studies are not that much extensively done in carbon-rich stars, but mostly in oxygen-rich stars with SiO and H2O. So this is something we would be interested in doing in the future. And which brings to the end of my talk. And that is that we have, just to give a summary, that we've studied 16 carbon-rich sources with different properties, observed them, and detected a number of vibrationally excited lines with also discovery of 24 new measures. And these lines are tracing the higher innermost part of the envelope because of its high excitation values. And more detailed information on this star structure would be then found out by interferometric data by analyzing the ALMA data. So, yeah, thank you for the talk.
Great, thank you so much, Manali. Are there any questions for Manali? If you'd like to ask a question, you can raise your hand with the reactions, or you can post it in the chat. I don't see any hands so far. I had a question that, and I got really excited with your talk because you're probing exactly the regions that we get interested in for following the dynamics of the gas and where the wind is being accelerated. Yeah. And I saw that even for IRC 10216, which we have quite a high, it's a carbon-rich star, it has quite a high wind velocity, but you found a very low velocity, 5 kilometers per second or so.
Yeah. Expansion velocity was very
yeah. Low. So that's really, really interesting. And that's at the 8 to 10 stellar radii. So the wind is taking some time to get accelerated.
Yeah, it's quite close, to the star.
And I thought I saw a hand. Could you go back to the other plot where you had the 3 different epochs? I was wondering if this one. Can you say what the velocities were, the expansion velocities? Or I know that's really asymmetric, and maybe it's hard to determine. But how was that changing?
Expansion velocity, I have not checked.
Okay.
I'm sorry.
No, that's okay. We're just really interested in how it changes with time, because really we want to see what the dynamics is doing at that part.
It was quite interesting to see the velocity peak has changed or has gotten low in intensity quite dramatically. You can see the major line. Yeah. Yeah, I should check that. Thanks.
It would be super, super interesting. The other thing that I was interested in is HCN. You can correct me if I'm wrong. HCN traces more the denser gas than CO would, for example. Is that correct?
Yes, I think so. Yes.
Yeah, it would be interesting to see how they compare and see whether we start to see more clumpy structures with the HCN or not, and how those two sort of, the scales compare for structures that we see with those different molecules.
Yeah, I think it's possible. Probably in the interferometric data, we can see more of this, what you're saying, especially high J transition, probably, yes.
Yeah, good. If there are no more questions, then we can carry on. Thank you very much, Manali, for a very super interesting talk.
Thank you.
Right where we need to, and very good timing too. So you kept us on track. Thank you.
Thank you.
Good. And our next speaker will be Sofia Wallström, who's at KU Leuven. So if Sofia, yeah, there you are. Would you like to share your screen? Let's make sure all of that is working. Yep. We might give it just a few minutes because I want to try and keep on the schedule in case people are joining a little bit late. So we might just start the screen sharing and see how we go. Let me just move that. I don't see any other questions. And we'll just wait a couple of minutes, I think, before we start with your talk, if that's okay. Thanks.
Hi, Shazreen. Can I just ask a quick question?
Certainly. Perfect. Yes, go ahead.
So I was going to ask this in the chat, but I missed what the frequencies of your masers were, Manali. It was a great talk. But what I'm wondering is that if one could do close epoch monitoring of the masers, we could use them to trace the dynamics in the sort of zone of a few stellar radii, like we can with SIO masers around oxygen-rich stars. But I think for that, they would need to be below about 129 gigahertz. So something like the Korean BLBI network could observe them. What were the lowest frequencies of your?
Oh, it was 2 to 1. It seems so 177 gigahertz.
Okay, but maybe there'd be more lower down in future, or maybe we'll get BLBI going up there.
Yeah.
Thank you.
Good. Are there any more questions for Manali, or anyone want to make a comment? Okay, if not, I think that we can start to have our next speaker, Sofia, if you want to come, and we'll maybe be a little bit a few minutes behind ahead of schedule, but I think that should be okay. You can at least introduce yourself properly and pronounce your name correctly for everyone. Okay, go ahead. Thanks so much, Sofia. You'll be telling us about the Nearby Evolved Stars survey and the dust and gas return to the galactic interstellar medium. So looking at gas and dust from AGB stars. Thanks so much, Sofia.
Thank you, Shazreen. So yes, I'm talking about the NESS project, Nearby Evolved Stars survey. We're an international team, so I've just named some people. Peter Cicluna is the PI. But yeah. So we want to study the dust and gas return to the interstellar medium in general. So ideally, we would observe all the stars in a galaxy, as has been done for the LMC and the SMC, for example, with Spitzer. So they get all the evolved stars by their colors, and they can really probe the dust return from these stars. That's not really possible to replicate in the Milky Way because of extinction. So we've turned to looking at mass return from the CO emission instead. And since we can't observe all the evolved stars in the galaxy, we want to have a sample delineated only by geometry to minimize the biases and be able to accurately characterize the population, or as accurately as possible. To do this, we need accurate distances, and that's the biggest stumbling block so far. But with the advent of Gaia, this is really helping. So in building our volume limited sample, we started with the IRAS point source catalog to cover almost all of the sky. There's a few slivers missing, which we will have to fill in other ways. So we've chosen sources consistent with AGB colors and then gone through manually and rejected sources with SEDs that show their YSOs or other contaminants. As I said, distance is often a problem because parallax measurements are made very difficult by the convection, dust scattering, and red colors of AGB stars. So we have used the Tycho Gaia astrometric solution, Hipparcos, and maser distances where possible. For stars where that is not available or has very large errors, we've derived a luminosity distance by assuming the same luminosity distribution as AGB stars in the LMC using the SAGE data. So we're hoping this is a more reasonable luminosity average to assume. We also calculate dust production rates from SEDs using the grams models, and then delineate a sample by distance and dust production rate. So altogether, this makes NESS, the Nearby Evolved Star Survey, the largest volume limited and statistically representative survey of AGB stars in the solar neighborhood. So we have about 800 sources within 3 kiloparsecs. It's a wedding cake style survey. I will show you the tiers based on distance and dust production rate. The aim is to observe all these sources in CO and submillimeter continuum so we can constrain both the gas and dust content. And we have an open science philosophy, so we aim to be fully reproducible and open source, and we'll release our data and scripts and everything upon publications. So here is the sample. So you can see the different tiers. There's 4 main tiers in distance on the x-axis and dust production rate on the y-axis. There's also the extra tier 0, which includes sources where we only have an upper limit on the dust production rate, so very low dust sources. Also outlined in black is a mapping sample where we're also getting maps of these fairly bright nearby sources to look at the distribution of the gas and dust as well. Here's the same source plot, but as a sky view, so you can see how they're distributed throughout the sky. It's a pretty good coverage. There's some clumping towards the galactic center, of course, but that's reasonable. So coming back to the distances, we've compared our distances that we're using with Gaia EDR3. And there's a line showing the one-to-one comparison here, and then 25% uncertainty. And the different colors represent the different styles of distance determination that we used. So largely the nearby sources, our distances are good, but as we get further away, there's more scatter, which is not unexpected. The size of the circles indicates the precision of the Gaia measurements. So a lot of these scattered points at large distances don't have very high precision from Gaia. So we feel justified in using our distances. But as the Gaia solutions improve, we will move our sources between tiers as necessary to reflect their adjusted distances. So the observations for NESS includes many, many hours of JCMT time, as well as APEX, Nobiama 45 meter, and some ALMA time. And we are, of course, using archival data where it's available and reasonable to do so. Overall, our observations are about 50% complete. There was a bit of an interruption to our extensive JCMT observations in 2019 as they upgraded their heterodyne receivers with the new Namakanui suite. but the new receivers are much more sensitive, so overall we haven't really lost any observing time. So as we only have about 50% observations, most of the results I will be moving on to now are preliminary. This, however, is published data. So Taïssa Danilovich looked at the UANT observations that we got with the Scuba 2 instrument onto JCMT and also compared it to Herschel data. So here we can see from top to bottom 70 micron, 160 micron from Herschel, and then the 450 and 850 micron data from the JCMT. And in all of them, well, the 450 micron is quite noisy. We can see that there's a peak in the dust around 40 arc seconds, and this matches what previous studies have found. At 850 micron, we also see a secondary interior peak at around 20 arc seconds, which may be a separate dust shell or just substructure in the larger dust shell. Moving on to our preliminary results for all the continuum data so far. So we have a lot of sources where we only have upper limits, generally at 450 micron, because it tends to be harder to get the necessary depth and sensitivity there. But we have a fair number of sources detected at both wavelengths as well. We've plotted on the left here the excess over the grams predictions. So 450 micron is on the y-axis and 850 on the x-axis. And as you can see, most of our sources have an excess over the grams predictions. This is not surprising because the grams models are based on optical to mid-infrared SEDs, and Sundar Srinivasan is working on extending the grams models to also include these sub-millimeter observations. On the right, we can see the 850 excess plotted against the dust production rate. And the black points, which are in both graphs, are sources where we know we have spatially extended sub-millimeter emission. So there seems to be a bit of a link between the spatially extended sources and the excess emission, which could indicate we have cold dust reservoirs, which is what we sort of expect to see and hope to see. We also see that there is more excess as you go to higher tiers and higher dust production rates, which also makes sense because these sources are then more likely to have cold dust. Since we have 450 and 850 micron data, we've calculated sub-millimeter spectral indices, which are shown here on the left. The alpha value of -2 has a dashed line, which indicates black body emission, and the one at -3.7 is the canonical value for interstellar dust from Planck. So most of our sources are consistent with black body emission from cold dust grains. There's two significant outliers, one at a small value for alpha, or a positive value for alpha. This is IC 418, which is a planetary nebula with significant free emission, which explains why it's doing this. And the stranger one down here at -7.4 is AK Hydra, which by all accounts seems to be just a normal nearby low mass loss rate AGB star. This strange spectral index could be due to a strange dust composition or an unusual size distribution. This is definitely something we will look into further. So as we said, we wanted to look at the total dust production rates in the solar neighborhood, and we've used the dust production rates that we have measured so far to look at this by tier, so lowest to highest dust production rates and also corresponding distances. So overall, our dust production rates that we find are consistent with previous estimates, and they're dominated by the high dust production rate sources as we expect. So moving on from the continuum observations to the CO emission, these are some of the mapping sample where we have a view of the extended CO emission. So 18 of the 25 mapping sources we've looked at so far, there are more coming, are extended beyond the 14 arcsecond beam of the JCMT telescope. So 2 examples are shown here, W Hydra and SW Virgo. The beam, the PSF of the beam is shown in red, and the excess emission is shown above. In SW Vir, we see some discrepancy with other results. We find that it extends out to about 30 arcseconds, which is twice the photodissociation radius found by Death Star using ACA data. So it'll be interesting to compare our results to results from other telescopes. From our more extensive staring sample, where we just have a single CO spectrum centered on the star, we have calculated empirical mass loss rates as a first estimate. So we have 280 sources so far with CO detections, and we've used the mass loss rate formula from Ramstedt et al. 2008 to get an initial estimate. But as you can see, there are large error bars on the mass loss rate here. So comparing that to the dust production rate, we get an idea of the gas to dust ratios, and they are largely consistent with the canonical values of 100 and 200 so far. There are more outliers at very low and very high dust production rates, which is again, not surprising. And the next step is to model all of these sources, all of the CO data, to get more accurate estimates of the mass loss rate. We've also compared this empirical mass loss rate with the expansion velocity that we find. That one is much more straightforward to measure from the spectra. And we've compared it to the Darwin models, and we find largely good agreement. So Sarah Blad presented the Darwin models on Monday. They're basically theoretical 1D models of AGB stars, both C and M-type stars. We find that our empirical mass loss rates are a little bit low and the errors are large, so it's a little hard to tell, but overall the agreement is not bad. There is, however, this strange lack of sources in this gap with velocities more than about 20 kilometers per second. And we will, look into why that might be. I don't know if it's just the sources we've happened to observe so far, or if we just aren't finding sources in this gap. So to summarize, the objectives of NESS is to find the total mass return to the solar neighborhood, and also to do statistically robust studies of evolved star physics with our large sample. We hope to become a go-to database for nearby evolved stars. The data collection and analysis is ongoing. There's still a lot to do. We have an overview paper that is currently under review, so hopefully you'll be able to read that soon. There's also catalog, heterodyne data, and CO1-0 papers in preparation. There is general information, and there will be the catalog published at the NESS website at evolvedstars.space as papers are published. Thank you.
Great, thanks so much, Sofia. Questions for Sofia, perfectly timed. I was just about to give you a 2-minute warning, so that's good. Questions for Sofia and about NESS? I see one hand. Patricia, please go ahead.
Thanks very much, Sofia. Nice talk and very interesting work. Could you just comment on the variability characteristics of the stars that you've selected? Are they predominantly Miras, semi-regulars, or what?
We have the full range of variability, I assume. A lot of these stars are actually ones that haven't been extensively studied before. Like not even CO spectra exist. So for a lot of them, we don't know this information yet. We don't really have the ability to look at the variability of these stars. We're generally not observing them over multiple epochs. So that is a drawback.
Okay, thanks. And I presume there'd be a bit of a difference, that there will be graduations with distance, given that they're essentially an IRAS selected sample. You will be seeing significantly different stars at the larger distance.
Yes, we definitely have the dustier stars at higher distances.
Thank you.
Good. Sofia, go ahead.
Thank you, Sofia, for this interesting talk. We're very much looking forward to the next paper with the overview of all the results that you have so far. First, I have to comment that you did this comparison with SWVIR, and there is no photodissociation radius in our paper calculated from the data.
Okay.
So I'm curious to know what you actually compared to. If you did compare with the calculations that we do, it's the size of the CO2 to 1 line, which is indeed a factor of 2 smaller than the photodissociation radius or something of that sort. So
Okay.
then if that is the case, then our results should actually be consistent. But that's just a comment. So the other question that I had was, you showed this comparison between your empirical mass loss rates to the velocity diagram and compared it to exactly to the Darwin models. I was curious to know if you compared your empirical estimates to any of the full radiative transfer model estimates of some of the overlapping sources, either from our results or from the results of Elvire de Beck, for instance.
Yeah, that is definitely on our to-do list to compare our data with previous results, but it takes a bit longer to do. This was a simple
so you didn't do that
initial
yet?
step.
No, that might explain why all of your sources end up at a lower mass loss rate, because the full radiative transfer models do overlap with the Darwin models, as I think Sarah showed in her results.
Yeah,
all right.
I would expect them to.
Okay, thanks.
Thanks, Sophia, and maybe you want to stay on. There's a question in the chat from Tom. Tom, do you want to ask your question, or should I go ahead? Okay, I can ask it. He says, what are grams and Death Star? So Sophia maybe can say about Death Star. Oh, both are Sophia's. Sofia Wallström. Sorry, Sofia Wallström. Could you say a little bit more about grams?
Yeah, so grams is a grid of AGB and RSG models that were developed by Sundar Srinivasan and Greg Sloan and others that basically take an optical to mid-infrared SED and fit a dust production rate based on the SEDs measured for various stars. I think it was developed from the SAGE data. So
great, thanks, and thanks, Ian, for putting these in the chat, the links to those. Sophia, do you want to? Sophia Ramstedt, can you say a little bit more about Death Star? I know that there's a poster also in GatherTown that you can look at about that.
Exactly, there's a poster by Miura and Sayalasa in GatherTown. I forgot which number it is. It's a low number at least, and it has Death Star in the title. But it's our project that we started some years ago on ALMA to map all the nearby AGB stars in CO, and it's in some sense overlapping with NESS, but NESS goes a lot further out and does sources that have not been detected in CO before, while the sources that we are looking at have previous CO detection. So there is some overlap. And we're starting to do our radiative transfer modeling right now. But I also wanted to say, now that we're on it anyway, and the grams models are up, I could comment to say that we see similar results with having higher fluxes in the submillimeter than what you expect, perhaps from SED modeling. But I need to say that you have to be extremely careful at these wavelengths because the dust properties are not well known. So that is something that you have to take care with when you do this type of analysis. And this is something that we're working on right now. So there is more to come on this. All right,
yep,
go to 7. Yeah, thank you, Susanna.
Yeah, so Susanna says Miora's poster is number 7, and thanks Stefan also for saying that. Any other questions on this? Thank you for this really great talk and good discussion. We can have our next speaker, and Tom says thanks, his question is answered, so that's good. Thanks so much. Our next speaker is Frederik De Ceuster, and he can share his screen.
Yeah. So can you all see my screen now?
Yes, we can see it great. Okay, so Frederik is from UCL and KU Leuven. And now we have already heard about people going to work on the radiative transfer, or we have a tool being explained for us, Marguerite, beyond the treachery of images. Go ahead, Frederik, thanks.
Okay,
I'll give you a 2-minute warning before your 15 minutes.
Okay, perfect, thank you. So thanks to the organizer for this opportunity to present my work here. I'm Frederik De Ceuster, a final year PhD student at University College London and KU Leuven. And over the past 4 years, I have been developing Marguerite, the radiative transfer library, in collaboration with all the people listed here below. And in particular, I would like to highlight our 2 master students, Thomas Keulemans and Atoly Tsirivastava, who have contributed to the most recent developments in Marguerite. So radiative transfer plays a key role throughout astrophysics, but today I would like to highlight its particular importance for stellar winds around evolved stars. So recent ALMA observations by the Atomium Consortium, such as this one by R. Aquile, allows us to study stellar winds in their full complexity. Now, in order to understand how these structures are formed, we need modeling tools that can handle this complexity. So that means a tightly coupled 3D hydrodynamics, chemistry, and radiative transfer model. And it's important to note that these cannot be seen as 3 separate models, but that they are highly interdependent. So for hydrodynamics, for instance, radiation acts as an efficient cooling mechanism and as an additional pressure term, whereas for chemistry, it results in photoreactions. So in a sense, it is radiation that will determine whether the stellar material can cool enough and is shielded enough from radiation, such that complex chains of chemical reactions can take place to form dust, and that can then be driven by radiation to launch a stellar wind. So in this talk, I will focus on line radiative transfer, although we are also working to include continuum radiation and scattering. As I'm sure you all know, lines originate from transitions between quantized energy levels of atoms and molecules, causing distinct narrow features in emission and absorption spectra. These are so narrow in frequency that they are very sensitive to Doppler shifts, causing a strong connection between the radiation field and the velocity distribution. Now, in addition, the radiative properties of the medium depend on the radiation field themselves, resulting in a strong nonlinear coupling between the two. And as a result, the radiation field has to be computed in an iterative way, commonly known as lambda iteration. Now, if you can observe and identify atomic and molecular lines, they encode valuable information about the composition, temperature, and the velocity of the medium, making them ideal probes to study, for instance, interstellar wind morphologies. In order to model these, we developed Marguerite. Now, of course, you can ask yourself, why did we build yet another radiative transfer solver? Because admittedly, 5 years ago, there were already several 3D radiative transfer solvers available. So why build yet another one? And the reason was that none of the existing solvers could provide all the critical features that we were looking for. First of all, we needed a solver that was designed as a plugin. So since our ultimate goal is to couple radiative transfer with hydrodynamics and chemistry models, and coupling codes is often not trivial. Now, in our group, we work with both grid codes such as Amarvac, which is a hierarchically refined grid, and particle codes such as Phantom, which is based on a smooth particle hydrodynamics, or SPH. If we want to be able to couple to both, we need a very flexible design that requires minimum assumptions, and in particular about the grid structure. Then, second, we want to be able to leverage modern computer hardware. So radiative transfer is computationally very demanding, and the only way to run it in an acceptable time frame is on, well, basically so-called supercomputers. Modern supercomputers are dominated by 2 main trends, parallelism and accelerators. So this means that we want our code to efficiently run in parallel over the multiple cores inside the processor and the multiple processing nodes inside a cluster. Now, apart from regular CPUs, a modern cluster also contains accelerators such as GPUs or FPGAs, which are much faster for some specialized operations. So therefore, we also want to be able to offload our computations to these accelerators. And then finally, I require a fully benchmarked performance in terms of accuracy, computational speed, and scaling. Since we aim to do large simulations requiring large computational resources in which many parts of the computation depend on radiative transfer. So yeah, if we invest all this time and resources, you at least hope that the results are reliable. And as I will show a bit later, we're currently actually trying to go a bit further than that by also trying to provide uncertain quantification on all our results. So with these requirements in mind, about 4 years ago, we started building Magritte. So how does it work then? Now, the first and foremost feature is that we do not assume any type of grid structure. So we use a meshless model geometry. This means that we assume a point cloud in which we only know the position and the nearest neighbors for each point. Then, given this model, the radiation field is computed with a deterministic ray tracer and a formal solver, meaning that we trace rays, or just straight lines, through our model, and then solve the radiative transfer equation along those rays. Now, since we want to do line radiative transfer, there's a strong coupling between the radiative properties of the medium and the radiation field. So as a result, we iteratively have to compute for the radiation field until these radiative properties converge. Now, there are plenty of tricks to do this in a clever way, such as accelerated lambda iterations, ing acceleration, and multi-resolution solvers. And some of these are already implemented, and some are still under development, as I will explain a bit later. Now, since the main contribution to the computational cost comes from the fact that hydrodynamics models that we use as input contain such an awful lot of points, we asked ourselves, whether we actually need all of these input points? And it turned out that if you properly resample the remaining points, that the required number of points can be reduced by about an order of magnitude without significant loss of accuracy on the radiative transfer results. So we verified this both for adaptive mesh refinement models, such as this Amorvac model that you see here. So this is the initial density distribution done with the original mesh. Then this shows reduced mesh, which contains about an order of magnitude fewer points. And then this is the implied error, which is, well, reasonable. We also checked this for smooth particle hydrodynamics models, as you see here, where we see even lower resulting errors. Now, for all details on what it actually means to properly resample the remaining points and how to construct these grids, I can refer you to our 2020 paper. And then finally, all of the above is implemented in an MPI OpenMP hybrid and able to leverage both multi-thread and multi-node parallelism as well as GPU offloading. So what does Magritte have to offer for stellar wind research? Although we already made considerable progress in making radiative transfer computationally cheaper, we are not yet at the point where we can afford to run full radiation hydrochemical models. Now, nevertheless, we do have a roadmap to make that possible over the next 4 years. Now, in the meantime, we can already use Magritte for post-processing hydrodynamical models and make synthetic observations. So here we see some synthetic observations sweeping through frequency space in the channel maps of the first rotational transition in CO for 3 different smooth particle hydrodynamics models by Silke Maas and Jolien Malfay. These models show the effects of a companion perturbing an AGB wind and help us understand how the resulting wind morphology can be understood from the companion interaction. Now, to learn more about these great simulations, definitely check out the posters by Silke Maas and Jolien Malfay. You can find it here in Gathertown, and keep an eye out for their papers that will appear soon in ANA. So what do we see here exactly? The left column shows the observations along the x-axis, so viewed directly at the orbital plane. And the right column shows the observations along the x-axis, so looking into the orbital plane. Then, as I also already mentioned, we can do the same for adaptive mesh codes, for which we see an example here by Jan Bolte. So also here, we see the interaction between a companion on an AGB wind, but this time modeled by Amorvac. And here we first briefly saw the hydrodynamics model, and now we are turning through the model, our rotating model, and look at it at different angles and then sweep through the different channel maps again. And here we see a slightly more complicated velocity structure arising already. Good. So for now, we only have been able to use Magritte as a post-processing tool to create synthetic observation, but we're working hard to dramatically reduce the computational cost of these models and to couple them with hydrodynamics and chemistry. But how are we going to do that? So basically what we answer, is what is next? So together with our master students, Adolit Silva and Thomas Keulmans, we have been working on Magritte 2.0. Now, this new version will be faster and will provide uncertainty quantification on the results. This will allow us to push performance further while knowing what the implied cost is in accuracy on the models. Yeah, in the first project, we are trying to improve ing acceleration. So ing acceleration is actually just a mathematical trick to improve the convergence in the iterative computation of the radiation field. And you can find it in basically every book and almost every solver for line radiative transfer. So now we notice that exactly the same mathematical trick goes under various different names in mathematics and computer science literature, where it's used, for instance, to accelerate training in machine learning applications. However, they often formulate this trick in a slightly different way, which makes it much more flexible and powerful to use than any implementation we've seen so far in radiative transfer applications. So how does it work? Now, classical ing acceleration, for instance, for order 4 goes as follows. So starting from starting from an initial iteration, we first perform 3 regular lambda iterations. And then there is a special iteration step in which we make a prediction for the fixed point based on the previous 4 iterations, like this. And then again, we perform 3 regular lambda iterations until we have 4 new iterates and can again do this special iteration step, predicting the fixed point based on the previous 4 iterates. And then this is repeated until convergence is reached. Now, in general, this iterative scheme will have better convergence than just regular lambda iterations. But the problem is that you inject a predicted solution in your lambda iteration without knowing whether the prediction is actually any good. And also the order is fixed and is quite arbitrary. So it might very well be that for your particular problem, it's better to use 5 or 6 previous iterates. In our improved scheme, we address this as follows. So we make a prediction for the fixed point at every iteration, but do not inject it into the lambda iterations. So you just store them in parallel with the regular lambda iterations. And only when the predictions satisfy a certain convergence criterion, then we will inject it in the lambda iterations. And well, depending on the convergence criterion that you use, this usually immediately implies convergence of the lambda iterations. Now, if not, you can of course always repeat this procedure. Now, this simple tweak allows us to use the ideas of acceleration of convergence in a much more effective way, reducing the computational cost roughly by a factor of 2 to 4. Then another thing that we are exploring in this project is emulation. So here we ask ourselves whether we really have to compute the radiation field in the entire model, or whether we can just do the exact computation only for a fraction of the model, and then use, for instance, Gaussian process interpolation to emulate the results on the remaining part of the model, giving us a cheap way to get past these expensive computations. Now, it turns out so that we can push this quite far, especially if we also include derivative information into the Gaussian process, resulting effectively in a hybrid between a long and a short characteristic solver. Then in another project, together with Thomas Keulemans this time, we're exploring the use of multi-resolution methods. So this is somehow similar to the idea of the emulator, but applied here over multiple iterations. So the radiation field has to be computed in an iterative way, meaning that we have to compute it over and over again while the radiative properties of the medium converge. Now, the idea of multigrid is that instead of computing the radiation field over and over again on the intricate fine mesh, that for the first iterations, which aren't exact anyway, we iterate on a much coarser version of the mesh and then gradually move to finer meshes as the solution converges. This reduces the overall computational cost, since the iterations on the coarse meshes are much cheaper.
2 minutes.
Okay, thank you very much. Then finally, so we're also looking into a truly probabilistic way to do radiative transfer that naturally allows for uncertainty quantification. So a severe shortcoming of all existing radiative transfer solvers is that we have absolutely no idea about their uncertainties. So we always assume their solutions to be exact and present them without error bars, while we know very well that there are uncertainties propagating from the input data and uncertainties due to the discretization errors in the solver. So this is obviously an issue when you want to draw any conclusions from radiative transfer results or when you want to make any predictions. But it also makes it hard to push performance since we cannot properly gauge the trade-off that we're making between accuracy and speed. So therefore, in this project, we propose a new, truly probabilistic solution scheme based on probabilistic numerics. So that allows us to compute radiation field as well as its uncertainty. And we do this by modeling the probability distribution over all possible solutions of the radiation field, conditioned on the radiative transfer equation and the corresponding boundary conditions. Now, this might sound prohibitively computationally expensive, and in general, it is. However, if you assume a Gaussian distribution on the errors, it can be done in a relatively feasible way. And all of this will be combined into Magritte 2.0, which will be a fast hybrid solver emulator with uncertainty quantification. And this will allow us to model the full complexity of the current observations and hopefully get beyond the tree of images. So yeah, thank you very much. That was all from me. And definitely check out the posters by Silke Maas and Jolien Malfai in Gathertown. Thank you.
Great, thank you so much, Frederik. Questions for Frederik, please raise your hand or you can type them in the chat. I see Sofia has a question. Please go ahead, Sofia.
Thank you. I'm sorry to hog the question session. Maybe I'm the only morning person among a whole bunch of astronomers. Thank you for this interesting talk, Frederik. It's very nice to see such nice results. I was wondering, so we've in our analysis of ALMA data, when we try to do it in 3D, we've been using, in one example, we've been using SPH model hydrodynamics and putting it into LIME. And we've also used output from shape, where you can construct an arbitrary shape and assign it with the temperature structure and density structure, and also run that through LIME. And I assume that you're familiar with LIME since you're using it in your group as well. Yep. But so my question, so the problem that we have is, of course, that we're not including radiation from a SAR or a radiation field from the dust within the CSE. So I was wondering, so you mentioned that you don't have continuum in the beginning of your talk, but then you didn't come back to it. So I was wondering if you're going to do something about that part.
Yeah, so currently it is possible to add continuum radiation in the simulations already. So for instance, you can put a stellar spectrum, or you can like put continuum radiation at the surface of the star, for instance, and take that as boundary conditions. The main thing that we don't have right now is scattering. So that's the main issue with continuum radiation that we're dealing. But yeah, so as boundary conditions, it is possible to include continuum. So for instance, by the star or by the exterior.
Okay, so it's yet not possible to do it for like dust that is spread throughout your structure, or?
Yeah, so just a source of continuum radiation, so dust particles sourcing the radiation field, that should be possible. Yeah, that's also possible.
Oh, okay.
Yeah.
Cool, thanks.
Good, are there other questions? Along those lines, I was also wondering, I always have binaries on my mind. Sorry, is it possible to put in radiation field from a companion nearby?
Yeah, sure. So you can, so in our models, you can basically define the boundary of your radiation field wherever you want it. So if you put if you like define a boundary around that companion object, you can also like define a radiation field originating from there. Yeah, so that would be possible.
So you'd be able to have two boundaries, so one around the AGB star and one around the companion.
Yes, exactly. Yeah.
Good. That's exciting. We have a question from Sync. Please go ahead.
Could you share about the programming time, computing time of the program? How long does it?
Yeah, that's a good question. So I think, yeah, so in our 2020 paper, there we had comparisons of the computing time with the original version of the code. So currently we're working hard on the crank up performance of the GPU implementation, so the numbers that are presented there are actually lower bounds on the performance, or upper bounds on the computing time. So yeah, it really depends on the size of model that you're looking at, of course. But let's see. So for the 3D structure that I showed, yeah, let me show the images that I showed with the reduced models there. So there, for a reduction of the model that contains about, what was it, 30,000 points, I think, that would take, if you want to do full non-LTE modeling, that would take about a day, I think. Yeah, well, a day or two. That order of magnitude, depending, of course, on which molecules that you include, and then yeah, because it very much depends on the type of molecules you include, the number of points you have, and then also the number of rays you need to properly sample all directions, because that also depends on, well, the type of model that you have. If you have a very regular model, you can probably get away with only a few rays, whereas if you have a very intricate model, you need like high directional resolution. But yeah, I am planning, like in the future, to have on our website and on our in our documentation some way to compute how long a certain model will take, and then, like, given an input model that you know upfront how long a simulation would possibly take, because I know that, like, it's important to know that in advance, that you don't wait forever for things to converge. But yeah, I'm sorry, I can't like give you a simple answer right now about this.
Thank you.
Great, thanks. If there are any last, I have a few more questions, but I'm going to put them in the Slack channel for you, Frederik. If there are no more questions, I'd like to thank all of the speakers for today, for this morning session. Everyone kept it to time beautifully, so thank you all very much for that, and for the really, really good talks. As I said, we can continue the discussions on Slack. Before we head over to GatherTown, there are a few announcements. So the speakers for the next session, the Zoom will open 15 minutes before the start of the session, so people can test their screen sharing, and Theo will be the session chair for that. So you can join a little bit earlier, you have a shorter break. If you're attending the diversity discussion, you should have already received an email with the link for that, with the Zoom link. If you haven't and you signed up, please let us know. I think that should be it. I'll put the link here to GatherTown, but thank you very much, everyone, for really good session. Let's head over and read some posters, meet people, chat, and have some coffee. Great, thank you. Thanks, everybody.
Resume the recording. I see someone else did that already. Okay, and so we start with the invited talk by Libby Jones, talking about metal poor evolved stars in the JWST era. Olivia. Yeah.
Hello, good morning, everyone. Actually, good afternoon, good evening, wherever you are. Can you see my full presentation before we start? Excellent. Thank you for letting me talk to you today. It's an absolute delight, and especially as we are getting very close to the launch of JWST later this year. And it's so nice to be able to say later this year for the launch of JWST. Because of my focus is on the mid-infrared and infrared populations, I'm going to limit my remit to that area, but I would like to point out Sofia's talk earlier on today about nearby stars and then their gas populations, and then later on in the week, Steve Goldman's talk on metal-rich AGB stars. And also there's some very nice posters I noticed in the GatherTown on Gaia and populations of star formation history. So please check out larger populations of AGB stars, not just my biased infrared focus. So I don't think you can start talking about metal-poor evolved stars and populations of them without starting off talking about the Magellanic Clouds. These are two very nearby galaxies which have approximately a half solar metallicity for the LMC and about 1/5 solar metallicity for the SMC. And these nearby galaxies are great because every single star is at the same distance, and there has been many deep multi-epoch wide field surveys from the optical to the far infrared. And particularly for evolved stars, the SAGE survey has been able to detect a lot of AGB stars, massive stars as well, which are bright in the mid-infrared and producing lots of dust, which makes me a very happy person because I'm very interested in dust production from evolved stars and the chemistry of that dust. We also have a larger range of spectra to have a look more at the molecules and chemistry of the evolved star populations, and optical and other multiple wavelength spectra to have a very rich data set of which to look at the AGB star populations of these galaxies. Summarizing in one slide a large body of work and multiple papers, the SAGE team and many others have looked for the entire AGB population, modeled them using infrared excess colors or full ready transfer models or model grids to work out both the chemistry and the type of dust they're producing. And then that summed up the total dust production in the Large Magellanic Cloud. With the Herschel view and other measurements of the Magellanic Cloud, you also have an idea of the total ISM dust mass. We also have wonderful imaging of supernova 1987A, so we can have an idea of the quantification of the dust production, though there is still very large error bars in that. And so with all that information together, the sources and sinks of interstellar dust, you can work out that AGB stars account for a significant fraction of the ISM dust in the Magellanic Clouds, especially even if we take account grain destruction by supernova. And in the JWST era, this value is going to get much better because we are finally going to be able to have a high resolution look at supernova dust production, particularly looking at 1987A. And I'm very well, it's experienced a reverse shock. So I'm very happy to be involved in that program. So what we did learn is that the majority of dust producing AGB stars consist of a very small fraction of the total AGB population. And so what was really intriguing to me is that in the Herschel data and the bandmatch catalogue, there are around 500 evolved star candidates. And the beam size of Herschel is extremely big compared to SAGE and even compared to optical, and especially compared to optical data. So it was expected that less than 5 of these were going to be genuine evolved stars. But what happens if we were really missing some of these very few extreme stars that had a lot of amounts of cold dust? So using all the wonderful multi-wavelength data, I did a delta dive into this sample of bandmatch catalogue from Herschel, and we confirmed that 23 of these stars, which were detected in the far infrared, were evolved stars. And possibly doing this, I made one of the longest wavelength color magnitude diagrams you will ever see. The majority of the candidate evolved stars turned out to be young stellar objects, but several of them were spectroscopically confirmed to be evolved AGB stars. 2 of them were the ones that had the highest mass loss rates measured in the dust budgets, and both were carbon rich. But we also detected in the Herschel view the red supergiant WHG64, which Albert Zylstra commonly refers to as the monster, just how crazy it is. And then there was a few other AGB stars and evolved stars that had oxygen-rich chemistry. So what I wanted to do, it still wasn't clear if that dust was actually associated with the star themselves, or was it due to the large beam of Herschel or just surrounding ISM. And I'm sure some of you here were on the ALMA panel. I just want to show a quick look. We looked at the 5 brightest evolved stars detected in Herschel at 350 microns, and asked for both ALMA observations of the CO in band 7 and also the high resolution continuing view of the dust in band 9. And we were really surprised with what came back. So we detected the dust and in fact resolved the dust, and I hope you can see the black contours of this particular star in the image. So the black contours are the band 9 dust, resolved dust at the star itself, and then the rest of the observations, so the step through the data cube of CO and one of our sources. And just to put it into perspective, these are in the Magellanic Clouds. So we are seeing here one of these stars is crazy big. It's comparable to VYCMA in our own galaxy, and maybe even possibly a bit bigger in terms of the CO. And so it'd be very nice just to talk to some people later on in Gather Town who are more commonly used to looking at ALMA observations, because this is not what I was expecting to detect with ALMA at all. Moving on from that, because I want to go back to the mid-infrared view, and want to move away now from the magellanic clouds to where we were really pushing the limits with Spitzer. To look further around in the local group, it gets more challenging just due to the small telescope size of 85 centimeters that was Spitzer to look at populations as a whole. And so what many teams did was to look at variable star information, say at multiple epochs, and then try and use a variability index to look and find the evolved populations, which are long period variables. So McQuinn et al. In 2007 was one of the first to do this in the Galaxy M33. And then there's a very nice series of papers by Javadi and the group who then looked at long period variables to work out the star formation histories of galaxies or star formation structures. I don't have time to talk about those papers today, but there is a post on that method as applied to another local group galaxy. So I really encourage you to check it out. Other galaxies that are involved, there's observed with Spitzer, especially cold Spitzer, there's about 10 in the local group. But it's to have a larger sample. It was really warm Spitzer when you started to look at populations and pushing the limits of where you're detecting evolved stars. And so the dusting survey, led by Martha Boyer, did a fantastic job at this, looking at 50 dwarf galaxies within 1.5 megaparsecs. And these galaxies span a range of conditions, environmental parameters, and metallicity. And what the dusting survey did was found around 500 metal poor dust-producing AGB stars, which I think was absolutely fantastic, because it was unclear exactly how much dust, or if metal poor AGB stars can produce dust in significant amounts at low metallicity. So as we now know that the dust production is not inhibited in these low metallicity environments, unfortunately the warm Spitzer doesn't give you much chance to look at what type of chemistry that dust is. So there was a very nice method developed by Martha using the wide field camera 3 infrared filters with HST. And these filters are wonderful because they can very cleanly separate out carbon-rich AGB stars from oxygen-rich AGB stars. And the way this works is using particularly the F139 medium filter, as you can see in the top left-hand plot, which nicely traces the water feature in the spectra. So by using that H2O absorption, you can see this very nice long trail of M-type stars and their evolution. And it's very nice when models and theory agree with observations, because when that was put into practice for these metal poor galaxies, we got very clean results. So what I'm showing in the main figure in this plot is 4 galaxies from the dusting sample observed with HST, and then highlighted with the black triangles around them are the stars that were determined to be dusty with Spitzer, the warm Spitzer mission. And if you look particularly at Sextans A, 3 of those stars that are dusty are oxygen rich, which is a surprise. So it's very exciting to me, and I would absolutely love to look in closer detail at these stars with JWST to get the high resolution view both in imaging and spectroscopy. Because Sextans A, the metallicity is approximately 1/7 of the solar value. Just to confirm then that AGB stars, based on these values, can produce dust very early in the evolution of galaxies. So around, if you're assuming big, massive AGB stars, around 30 mega years after they first form. So this can mean that these evolved stars can contribute significantly to the dust reservoirs seen in high redshift galaxies. And so very nicely, I also had a data set from the work infrared camera in JHK for Sextans A. And Sextans A, luckily, was also one of the few galaxies observed with cold Spitzer. So by comparing the work data and the Spitzer data, you can construct spectral energy distributions of the stars in Sextans A. and then try and attempt to model them using radiative transfer models or grids of radiative transfer models, which we've talked about earlier today, particularly the Grams grid. So what I'm showing in the top panel is the SAD of one of these candidate dusty over-rich AGB stars. And then the blue is the best fit oxygen-rich model. The red is the best fit carbon-rich model. And the gray points are the range of models which produce an acceptable fit to the data. And so what you may see here is what we're really missing with the cold Spitzer data is the data stops around 8 microns, and it'd be nice just to have a few data points at longer wavelengths to constrain the amount of dust production. And then, so what we did do is we do have an idea of the amount of dust, but it's still large uncertainties on these values. And then nicely in a theoretical point of view, Flavia Danilovich followed up using her models of stellar evolution and dust production to have a look to see where these metal poor AGB stars are made producing dust. So that's what I'm showing in the bottom panel. The magenta tracks are the realm in JHK space versus dust production of where the hot bottom burning massive AGB stars that are oxygen-rich can produce dust. And the blue cyan tracks are where carbon stars can produce dust. And what I'm very excited to see is in the top panel, my object ID 210 falls exactly in the dust producing range for hot bottom burning stars in Sextant A. So it was very nice to keep us honest, observers honest, by looking at this and comparing to theoretical models. Though also there is a star in there of 264, which I thought was carbon rich, but it turns out Flavia thinks this is another massive oxygen-rich star that could be producing dust at some large rates. So I think Sextant A is a very exciting galaxy to be looking at in future with JWST. Changing tracks a bit, I am also very interested in the dwarf elliptical galaxy M32. So M32 is a very compact galaxy on the outskirts of Andromeda. And the reason why I was really interested in this galaxy to start off with is it has, as it's an elliptical galaxy, it has a large evolved star population, but it absolutely has no interstellar medium dust. So it's a very different environment to the Magellanic Clouds or spiral galaxies. With Cold Spitzer, we had a look and found a large population of extreme AGB stars that are producing dust, we think, at a large rate. But unfortunately, that data, there was no background observations. And as I said, it's very close by to M31. So it wasn't clear which populations these belong to. So I asked for some Spitzer time to look at the variable star population. And I possibly got one of the most challenging data sets I have ever worked with. And so what do you do with challenging data sets? You throw students at it. And I had two wonderful undergrad students working with me who did a lot of processing and reprocessing of this M32 data to make sure that we were getting, finding the AGB star population. So that, I want to shout out to Connor and Michael, who did a lot of work on this galaxy and wrangling possibly some of the most challenging data sets I have ever worked on. What we did find, though, is very nicely the infrared colours at 3.6 minus 4 microns showed a trend in amplitude, which corresponds to the redder stars, which Patricia Whitlock has previously noted. So I was very happy about that. So we were on the right track of detecting these large long period variable stars. But what really intrigued me is that the 4.5 micron data shows no similar trend with colour. And so Sarah Blah, who gave a talk on Monday, very happily computed for me some Spitzer colours, and the Darwin models show a similar trend, which made me very relieved. But I was also, I'm very interested in about what chemistry is going on in the atmospheres during the pulsation cycle to change, to show the different effects in these two Spitzer bands. If you compare the models, then we had a nice background field as well to have a look at what the M31 population was doing very nearby. And M31 had some massive stars, which M32 didn't. So again, it probably points to this old population, and it made me very happy that we were on the right track with looking at the evolved population in this galaxy. Using the same medium band filter method, we went ahead and found this to try and constrain the chemistry of these stars. And this worked again very nicely, and the data set compared to Spitzer was wonderful. So what we're seeing here is a large amount of M-type stars, and very few number of carbon stars. And this is currently a work in progress, but we're now need to work out just how many of those stars actually belong to M31 versus M32 to see if we may be reaching a metallicity ceiling for the carbon star formation. Also addressing that is working with another undergraduate student who I seem to throw at M32 a lot, I guess trial by fire. We're using a UK infrared telescope WIFCAM wide field survey. So this is about a 1 square degree field of view, looking at the satellites of Andromeda to look at the AGB star population. And then by looking at the carbon and oxygen-rich stars, you can work out metallicity gradients in these galaxies and have an idea of also the abundances and distributions of AGB stars, and actually learn more about the galaxy systems themselves. And so I think that's a very nice area in the Gaia era and wide field surveys to look at nearby galaxies. And then the final results from SPITS that I want to talk about today are the SPIRITS identifications of extremely long period stars. So SPIRITS since 2014 have started monitoring around 200 nearby galaxies, looking for transient infrared variables. They looked at around 20 galaxies, less than 10 megaparsecs, to try and identify the long period variable population. And what they used is over 10 epochs of data to find out the pulsation periods of these stars. And shown here are some color magnitude diagrams of 3.6 minus 4.5 against 4.5. And what is really standing out are these bright populations of thermally pulsing AGB stars in the red. Some of these, especially in the distant more massive galaxies, are exceptionally bright and have very long periods. So this is very exciting because it's wondering, are these population of super AGB stars? They follows on along the fundamental mode period luminosity relation, but extending to much higher luminosities and periods. And it's also been compared to candidate super AGB stars in the Magellanic Cloud. So I think this is a very interesting discovery space. Oh, thank you very much. So JWST is going to be launched very soon, later this year. It's currently sat in Norfolk Grumman. It looked absolutely beautiful, and we ship soon to French Guiana. And we have a large sample size to which populations to look at AGB stars. So I've talked about Sextans A, but I'm looking also at the nearby galaxies NGC 6822 and 1Zwicky-18. So NGC 6822 is a nearby galaxy. It's isolated though compared to Magellanic Clouds, so will have very different evolved star populations. And why we're interested in this is there's star formation going on and evolved stars. And Alec Herscher has been doing a lot of work using what we know from JHK and Spitzer data to find a new method using kernel density estimations to separate infrared stellar populations. And so we want to try and use this method of using the KDE minima to work out color hook boundaries rather than using just straight lines and by eye observations. So I'm very excited for using this method, given the large amount of JWST filters we have. Want to say that I put my neck out and think about what I think will be the best filters to see AGB populations. And I'm going to try that out with the guaranteed time data I have. I know many other people in the audience have also proposed different filters, so hopefully we're all correct and we're going to have a wonderful amount of science. And then finally, I just want to talk to you about the extremely metal poor galaxy 1Zwicky-18. So in most of this talk, I've talked about the Magellanic Clouds, nearby local group galaxies, but 1Zwicky-18 is an extreme galaxy at the very edge of this view. So just showing this plot here, it shows a metallicity of a host population on the bottom panel versus the gas to dust ratio of the galaxy. And 1Zwicky-18, which is 18 megaparsecs away, so this is going to really push the limits of Spitzer, falls right at the very bottom left of this panel. So this is going to be a very exciting population of AGB stars that we hope to detect. The total dust in the galaxy is measured to be around 560 solar masses, and the metallicity is expected to be around 1/50th of solar. With Spitzer, the view of 1Zwicky-18 is a giant blob. You have no chance of seeing its evolved star population, or in fact any populations at all. But 1Zwicky-18 has been observed with HST, and it turns out that 1Zwicky-18 is not just one galaxy, it's two galaxies in a very close companion. It's forming stars at a rate of around half a solar mass per year, and that's what you see in this big blue part of the galaxy at the bottom. But there's also, based on the HST observations, a significant AGB and evolved star population. So I'm very, very much looking forward to what we're going to see in this data set of extremely metal poor evolved stars. And I think at that point, I want to leave my talk there, just at the optimism of what the next decade will bring, both with JWST and the wide field surveys with Gaia, Euclid and LSST. I think it's a very exciting discoveries time for populations of AGB stars. Thank you.
Great. Thanks, Olivia, for this very nice talk. We have time for a couple of questions. So if you want to ask a question, please, you can raise your hands using the reaction button at the bottom there. Maybe I can, while people try to find the raise hand button, I can ask. So I was also surprised to see that you get these oxygen-rich sources in this very metal-poor galaxy. Is there a limit to like an expected theoretical limit to how far down in Metalist you can still get oxygen-rich mass-losing AGB stars, or do they always get enough metals to dredge up in some way to produce a wind?
So around an FE over H of -2, I think, is around the theoretical limit of where no dust is meant to be produced by AGB stars. That's absolutely nothing at all. And oxygen-rich AGB stars in particular is meant to be worse off than that. You're seeing a lot less dust produced by them in the Magellanic Clouds, for instance, and you're seeing different dust chemistries being produced in the Magellanic Clouds compared to what you see in the Milky Way, just due to different abundances of silicon and magnesium. So this, I think, took a lot of people by surprise when this was being hinted at, and I think theoretical models definitely need to catch up in this metal poor regime, and I'm really looking forward to see how theory evolves to compare with these observations. I'm very excited by this, and I think it took most of us by surprise, but pleasantly surprised.
Yeah, it's really interesting. I see that Shazrin has a question. Go ahead, Shazrin.
Hey, just related to a little bit of what you said about this low metallicity. So you mentioned these high redshift galaxies that have tons and tons of dust, 10 to the 8, 10 to the 9 solar masses of dust. And just given what we were discussing now with Theo, I mean, is it coming from AGB stars? Can we constrain that? How much do we expect from the AGB stars at that time in the universe? And will we get clues to this from Wandswiki 18, maybe?
I really hope Wandswiki 18 will do that. I think currently the working theory is most of that dust is produced by supernova. That is just assumed that because H7A can produce a lot of dust, this is how the mechanism to form it so early on in the universe. But it's still kind of unclear how much of that dust produced by supernova and massive stars will survive any reverse shock. So I think it's...
Yeah, exactly. So the massive ones have the problem and the AGB stars have a problem. So
yes, I'm really hoping Wandswiki 18 and the range of galaxies that JWST will observe will hopefully fill in a lot of parameter space and help us nail down the dust production models and stop things like dust being produced in the interstellar medium. I mean, that's a theory, or in fact, the disk of quasars.
Of AGN, that's
AGN.
The other one.
Yeah,
yes.
I really like that. And I'd actually like to see a lot more about dust formation than that, but then I guess that's moving away from AGB stars and looking at dust formation properties, which also very excite me.
Cool, thanks, good talk.
Cool, yeah, very interesting. A lot of things to look forward to with JWST. So thanks again, Olivia. And now we move on to Umberto Battino's talk on mixing and nuclear uncertainties in low metallicity AGB stars. You can go ahead and share your screen. Yeah, that's great.
So I hope you can see and hear me well, right? Okay.
Yeah. So I'll give you a 2-minute warning before then.
Thank you so much. Okay, so hello everyone. So I'm Umberto Battino from University of Edinburgh, a new collaboration indeed. So basically, as just announced, I'm going to talk about a recent publication about some assessment of the mixing uncertainties in low metallicity AGB stars. So I will first start, well, I think with a very, very brief introduction of basically AGB star internal structure, and why do we care about AGB stars, especially from a galactic chemical evolution perspective, which is basically the subject I care the most. So essentially, okay, AGB stars are, of course, the most important contributors of the galactic carbon, nitrogen, fluoride, but also important contribution for the sodium, magnesium, and also alpha the transition elements via DS process. Essentially, when you consider an AGB star, we talk about an internal, a central inert carbon-oxygen core surrounded by a shell structure where we find a helium burning, a hydrogen burning shell, and then a hugely extended convecting envelope. Of course, this image is totally out of scale. When we talk about it, we have a Earth-size, planet Earth-size carbon-oxygen core, and the hugely extended convecting envelope when compared to our sun. Well, that's what we're talking about, really. Most importantly, this hugely convective envelope, okay, as the word suggests, is fully convective, and this convective motion can also trigger some very interesting processes at the convective boundaries. One of those, for example, is the excitation of internal gravity waves. What you see here is not an AGB star, it's a massive star multi-D simulation, but you clearly see how the convective motion in the envelope can actually excite in the propagation of internal gravity waves, which are pretty much similar in totally similar in mechanism of the wave you excite on the surface of a lake when you throw a stone in it, except that these are basically surface gravity waves, these are internal gravity waves, but this is basically the basic mechanism. And this phenomena can indeed trigger mixing across the convective boundary. So where basically you should have in 1D prescription a Schwarzschild stable zone. And here we go. So the problem is that each of these internal mixing processes, such as, for example, the convective boundary mixing, but also the 1D description of convection, which is actually a multi-D phenomena, have important uncertainty, right? But for example, we do actually include convection in 1D, since still today, 1D is the only way to simulate the whole life of the star from start to finish. So we need to introduce some approximation as well for the convective boundary mixing. And for the convective boundary mixing formalism in AGB, those are validated usually only for around solar metallicity model, mainly because of the exceptional amount of observables. For example, we have a lot of pre-solar grains around solar metallicity. We can watch a solar metallicity carbon star, a barium star, but that's really around solar metallicity. That's where we have most of the observables. But then they are applied to the whole metallicity range. That's usually what people do, introducing quite a lot of systematic uncertainties down to low metallicity 1/10 and below the solar metallicity fraction. And this includes also the solar calibrated mixing length theory parameterization, for example, but which basically allows you to calibrate convection to reproduce the sun, for example. But the problem is not all the stars are like the sun, for example, especially low metallicity. So what I show here, talking about, for example, the synthesis of the heavy elements, transiron, which is the subject I really love. Everything happens really here in this tiny zone between the carbon-oxygen core and the convecting envelope. What you see here is the Kippenham diagram of a two-solar mass star from Herwig 2005. What you have here is basically the Lagrangian mass coordinate of inside the star. So every number tells you how many solar masses are underneath you. So you have the core of the star down there and the surface up here. And and basically what you have on the horizontal axis, you have the time. So you have the structure of the star evolving as a function of time. What you have here between the envelope and the core is the helium intershell, where everything happens concerning the synthesis of the heavy elements. So what happens is that when you have the hydrogen burning here and accumulates in a thin shell, so in thin shell instability condition, hydrogen burning ashes and helium, which when it's accumulated to a critical point, it basically causes a flash of the helium, basically ingesting all the nitrogen-14 produced by the hydrogen burning, converting it through double alpha capture into neutron-2, And this is basically, which is basically one of the main neutron source in the S process. And what happens at the bottom of this convective zone induced by the flash, you have a first convective boundary mixing right here. But then, as a result of this sudden release of internal energy, the envelope expands, cools down, the opacity goes up, and eventually convection becomes more efficient, penetrating inwards and causing a second convective boundary mixing episode here, induced by the so-called third ledge up, which basically brings all the heavy elements from the intershell to the surface and make them visible. So these are the two main convective boundary mixing episodes that happens and where they happen. Let's start from checking what happens from here. What I did in a recent publication, 2021, I consider basically a grid of 4 models, 2 masses and 2 metallicity, 2 crystal mass at 1,000 and 2 10 to minus 3 in a metal percentage. So the model you see here, what you have here on the y-axis is the elemental ratio normalized to solar of cerium over iron, and on the horizontal axis, cerium over yttrium. Cerium is our second peak element. Yttrium is our representative of the first peak element. And all these models basically are kind of the same, except for the different treatment of the convective boundary mixing under thermal pulse. Basically, the red, the blue, and the cyan are the same. The red one is the model by Rita 2018 with a little bit of convective boundary mixing there. The blue one is basically is my model, which simply slightly different from 2019. The blue and the cyan, the only difference between the blue and the cyan is the fact that the cyan is basically no convective boundary mixing under the convection, the thermal pulse flash, basically. And you see how basically this model is the one that is able to reproduce the highest portion of the cerium over yttrium covered by observation, which is basically the colored area here. The green is only basically a test I did with a different MRT prescription to get an impact of that, but the largest impact is given by the different convective boundary mixing prescription you adopt under the thermal pulse, the helium flash. So basically this happens because if you mix, basically, the less you mix under the thermal pulse, the less carbon you dredge up from the carbon to the intershell. And so the higher the helium fraction content will stay. The more helium you have, the lower the temperature you need to flash. And so basically, if you flash at a lower temperature, you basically, you activate to a lower efficiency, the branching point, which are here. These are a rubidium 86 and CRISPR-25 are 2 unstable isotopes with a time scale, with a lifetime on the order of years of days. And so they need high neutron densities to be overcome, to trigger a neutron capture on them and to produce rubidium 87 and CRISPR-86. Because basically at higher temperature you activate the neutron source. If you flash at a lower temperature, you mainly the neutron capture path goes through strontium 86 and proceeds. But if you flash at too high temperature, what happens is the neutron capture path will pass through 2 extra neutron magic stable isotopes, which are really then hard which offer a huge resistance to the neutron capture path to move on. And so basically, essentially, you accumulate a lot of first peak elements, in particular yttrium. That's why models with higher mixing under the thermal pulse with higher temperature produce negative cerium over yttrium, and those with a lower efficiency mixing under the thermal pulse produce a high, basically cerium over yttrium mixing. The problem is there's still this portion here, which is not covered by anything. So basically what we did, we tested a higher efficiency of the convective boundary mixing under the convective envelope, which is the one responsible for the formation of the so-called carbon-13 pocket. In particular, we tested a more efficient convective boundary mixing process, able to produce a 3 times wider pocket, so passing from typical size of 10 to the minus 4 solar mass in Lagrangian mass coordinate to 3 to 10 to the minus 4 solar mass. And the net result of this was basically we were able to the impact of this new convective boundary mixing prescription is visible here, comparing the Cheyenne model, which is the one I showed before, with the standard with the lower mass carbohydrate pocket, to all these ones, which basically have a large pocket up to three times higher. In particular, you compare the Cheyenne with in this case, the blue one, which are exactly the same except the larger pocket. I also introduced, for example, the purple cross, which are the literature results from the Teramo group, and also this black triangle, which is from the Monash group, which are fairly consistent. But you see basically that you actually need a convective boundary mixing and the convective envelope at least as efficient to produce a 3 times 10 to the minus 4 solar mass carbohydrate pocket to actually match the bulk of the observation, which are basically these stars, which are in the range of metallicity of the models plotted here. The only observation that are missed here are this bunch of stars here. So basically those stars showing a high cerium over iron, but a low, basically almost zero cerium over yttrium. We advanced some hypotheses for these stars. Those stars could actually be binaries maybe with a massive AGB companion who basically evolved through the AGB phase. In the case of massive AGB, basically the main neutron source there is the neutron is alpha n, so you produce a lot of first peak element, so a lot of yttrium, but almost very low abundance of second peak. And so basically, if you have a massive AGB companion evolving through the AGB and transferring the envelope matter on the surface of the main sequence companion, this will then start the main sequence with a starting negative cerium over yttrium abundance and then evolve through the AGB and ending up somewhere there. This is just a speculation, but a scenario that maybe could deserve some further investigation in our future work. So some conclusion and future plans. So those results have been published in Battino 2021, the Universe Journal, and model represented basically are comprise 2 masses, 2 3 solar mass and 2 metallicities. So 1 10 to minus 3, 2 10 to minus 3. And in order to basically, the main take-home message are, in order to be consistent with the observed heavy elements abundances, the low metallicity AGB model, you should include basically no or very small efficiency carbon convective boundary mixing model under the helium intershell. And and also talking about the convective envelope, instead you need to have a convective boundary mixing process at least efficient enough to form a carbohydrate pocket, or at least as large as 3 10 to minus 4 solar masses. That is required. The question is, in my case, I account for a convective boundary mixing which is calibrated on the effect induced by internal gravity waves. So the question is, well, are internal gravity waves actually capable to produce such a pocket? So this is work in progress. We know that they are for total metallicity model. We don't know yet if they are able in the low metallicity case. With this setting, our models show a final surface composition with a final cerium over iron between normalized to solar between 116 and 2, and a final cerium over yttrium between 0.6 and 1.2, which is consistent with the bulk of observations. And the only problem is how to explain this high cerium over iron and at the same time low cerium over yttrium stars. Could be by an evolution, so mass transfer from an evolved massive AGB companion on a less evolved companion. Yeah, this is an hypothesis to be investigated in a forthcoming paper. So as a final slide, just to let you know that also all these models, all the outputs, all the data are available, are publicly available online on the Globus, the NuGrid data repository, which is available on the NuGrid website, but in particular at this link here. So you just go there, you can grab them and do what you want. Thank you for listening.
Great. Thanks, Umberto, for keeping exactly on time. I didn't even have to give you the 2-minute warning. So we have time for a couple of questions. So if you want to ask a question, please raise your hand using the reactions button at the bottom. So maybe I can start with a quick question if, well, I don't know how quick it is actually. Can you go to your slide before the conclusions? Yeah, that one. So do I understand correctly that the type of parameters that you're varying between these different model tracks that you have here are should be the same for all stars, or do you expect variation between stars?
Well, that's a good question. So when we talk about convective boundary mixing, we are not talking stochastic process. We are not talking about translation, which is very static. If you compare the given metallicity mass, that is possible. Of course, one should do vibration for each mass metallicity pair. What I found here is basically a global setting which kind of work for at least the typical low mass AGB range with 2 and 3 solar mass, which are the main contributors for the S process in this case, right? So for that tiny mass range, this setting work. Of course, if you do go to a 4 solar mass, which basically is not the case of this object, because maybe when you go to 4 and 5 solar mass, you don't produce solar second peak elements. So you should have something else to validate your model. That may change. This basically is validated for low mass AGB regime. So 2 and 3 solar mass in the low metallicity case, of course, yes.
Okay, but so I missed a little bit of your question because either my connection or I don't know if it was your connection that was not working so well.
Sorry. Well, I mean, I think it could be mine. It could be mine.
Yeah, but then you would expect all observations to lie within one of these, or there might be mass and metallicity variations that affect that. I think I missed them.
Well, you can see here. There is a little bit of mass metallicity. If you compare the red model here, these are 2 solar mass. It is right here. The blue track is a 3 solar mass and 1 to the minus 3. So you have vibration, metallicity, and mass. You see the difference. And all the rest is the same. They have the same carbon pin pocket. You see there is an impact.
Yeah.
So of course you need some spread in mass and metallicity to cover the spread.
Okay.
And that's what I got.
Yeah. There's a question here in the chat, and it's from Meredith Joyce, and I'll just read it. My recollection is that NuGrid is integrated with a pretty old version of Mesa. Are there any plans to investigate with Mesa at a later version, using a later version?
Absolutely. Comparing for AGB stars, actually, okay, the older version works fine. So for AGB evolution, the older Mesa are actually good ones. So they're old but gold. That's what I said. But yes, indeed, there are plans to update to the newest Mesa revisions for many reasons. One also is to of course, when we talk about Mesa, we talk about a very active community which basically maintains certain revisions. So in order to keep up with the pace, we may also reproduce our results and produce a conversion in the coming future with the newest Mesa revision. Yes. Especially also for other scenarios, for example, for the binary evolution capabilities, which are not really as the same as in order ones. The rotation effect, those are substantially Mesa revision which are not there, but those mods are single stars, not rotating, and those works fine. But for the future edition, yes, definitely we plan to do that.
Okay, Meredith has another follow-up question here, but I invite you to ask it on Slack, Meredith, because we have to move on now. So thanks again, Umberto. You can talk to Meredith later. Yeah. So now we move on to Shreeya's talk on technetium rich low mass S stars and M stars. You can, yeah. So you can see a presentation now.
Yeah, I just forgot to unmute and unvideo myself or put my video on. Okay, here I am. Share my screen. Okay, so you should be able to see my screen now and in presentation mode. So
Perfect.
full screen.
So I'll give you a 2-minute warning.
Sure, thank you, thank you. So hello everyone, I am Shreeya Shetye and I would really like to thank the organizers for giving me this opportunity to talk about technetium-rich S-stars and M-stars. So let's get rolling. As we all know so far that the MSC sequence is the spectral sequence on the AGB, and this is quite a generalized impression of the MSC sequence on the AGB here in the HR diagram. I'll be focusing on the M stars and S stars, so mostly the oxygen-rich AGBs basically. Now, the characteristic features of the M stars is that you see titanium oxide bands in the optical spectra of these stars, and for the S stars, they are characterized by titanium oxide as well as zirconium oxide bands. The M stars, they have a carbon over oxygen ratio of almost 0.5, but the S stars, as has also been mentioned by Taïssa and previous other speakers, that they are transition objects between M stars and carbon stars. So they have a carbon over oxygen ratio in between 0.5 and 1. Now, for the first part of my presentation, I'll be focusing on the S stars, because these S stars, all of them, they reveal overabundances of S process abundances. So thanks to the previous speaker, I don't have to explain to you how these S process elements are made. We know that the AGB stars, they are full of these S process elements or heavy elements. And hence, if we want to understand this AGB nucleosynthesis or different processes which make these S elements, we can use basically these S stars as probes for that. But we have to be very careful because all S stars show S process elements, but not all S stars make these S process elements themselves. So this remained quite a puzzle actually for a long time when we saw technetium lines basically in some S stars while not in all of them. Until it was realized that S stars come in two flavors, the intrinsic and the extrinsic stars. So basically the intrinsic star, as the name itself suggests, they are intrinsically producing the S process elements themselves. So they are genuine thermally pulsing AGB stars producing the S process elements and also technetium. And the extrinsic S stars are polluted binaries. They owe their S process element abundances to a previous binary interaction with a former AGB companion, which is now evolved into a white dwarf. So these extrinsic S stars, they are close relatives to barium stars, CH stars, and they all belong to the same family of chemically peculiar stars, where they are not yet evolved themselves enough to make these S process elements. And this distinction for intrinsic and extrinsic stars can be made using technetium, as I mentioned, because it's a S process element with no long-lived stable isotope. So technetium really gives you the hints that the star is the genuine AGB star freshly producing the S process elements, which are brought then to the surface of the star because of the third Kirchhoff. So these S stars or the intrinsic S stars are definitely very interesting to us because we can use them to understand the third Kirchhoff physics, or even understand how the third Kirchhoff occurs for the first time and how it is related to the other properties like mass and metallicity of the star. I won't be talking about the extrinsic S stars, but we will definitely hear more about these kind of chemically peculiar stars in the next talk or in the talk of Anna Escorta tomorrow. So let's get again back to the intrinsic S stars. As I mentioned, they are extremely interesting to understand the AGB nucleosynthesis, but it is not pretty straightforward to perform a spectroscopic investigation of these S stars. For example, you're using optical spectra. I say this because the parameters of these S stars, they are strongly entangled with one another. So basically apart from the temperature and the log G, the surface gravity, there are many other parameters which also play a crucial role, which is the metallicity of the star, the carbon over oxygen ratio. So it's a multidimensional parameter space, and these parameters are strongly entangled with one another. So here I have plotted an example of the observed spectrum compared with two different models with completely different sets of parameters. And you can see that in many different spectral windows, in the optical spectral windows, it would be really hard to differentiate which model really reproduces the observed spectrum the best. And what I want to say is that the high resolution spectra itself is not sufficient to disentangle this parameter space of the S stars. So what we did is that we developed a methodology which makes use of the high resolution spectra, of course, but combines it with the Gaia parallaxes and also with some photometric indices to disentangle this parameter space of these S stars. I do not have the time to go into the details of the methodology, but you can definitely check it out in our papers. But you can also check that this method has been applied to different samples of S stars and has been validated through that. I will here give you a quick example or a teaser of a product of this methodology to also convince you that it works well. So here is an example of zirconium line and cerium lines. And you can see the agreement of the observed spectrum in black is very remarkable with the synthetic spectrum, with the synthetic spectrum of different abundances of zirconium or cerium. So you can definitely, we can definitely use this methodology to derive the accurate parameters, not only just that, but also then further to derive the S process abundances of these S stars and then compare them with AGB nucleosynthesis predictions. So I will get now to the results of our study. So the first and foremost thing you want to do once you have an accurate set of parameters is locate your stars in the HR diagram to check their evolutionary status. This is what we did with the technetium-rich as well as technetium-poor S stars using Gaia EDR3. What we found is that the technetium-rich S stars, they are located quite well beyond this predicted onset of the third threshold, which is marked by this black dashed line. So all the technetium-rich stars are located beyond the predicted onset of the third threshold, and the technetium-poor, they are the less evolved counterparts at the tip of the RGB or at the early AGB. So basically what we find from their chemistry, which is from their technetium features, is inconsistency, is incoherent with their location in the HR diagram or with their evolutionary status. Another highlight from this HR diagram was the discovery of low mass intrinsic stars. So these are stars with sun-like masses and sun-like metallicities showing technetium features and also abundances of other S process elements. So this is a hint that the third dredge-up is also active in these low mass and low solar-like metallicity stars. And this was not accounted for by the TP-AGB models, AGB models so far. So this is a nice feedback to the TP-AGB models and a nice constraint on the third dredge-up occurrence. Moving on. Here I am presenting some super fresh content, which where for the first time we've been able to measure the technetium abundances in a large sample of S stars. And we compared it also with we tried to find correlation of these technetium abundances with other stellar properties. In the figure that you see here, for 3 different stars with different masses and metallicities, you see that we have compared the measured abundance profile, so a technetium and also some other S process elements, with the nucleosynthesis predictions of that corresponding mass and metallicity. So we have quite a nice agreement, quite a good agreement, and it is pretty clear from the previous talk, right, that how these constraints, observational constraints, are very important on our nucleosynthesis predictions. So the example I have given you here is a very nice, well-fitting example, but of course there are still many gaps between the observations and between the nucleosynthesis predictions. And if you want to know more about these, then you can definitely check this paper, which got recently accepted in ANA and is on archive since last week. The final most, but a quite important highlight also from the S process abundances, which I would like to mention here, is the use of zirconium and niobium, the use of the zirconium and niobium abundances. So just to put everything in context, basically the niobium that we detect in the spectra of these S process enriched stars, so AGB stars, also the other chemically peculiar stars enriched with AGB material, S process material, this niobium, this monoisotopic niobium, can only be produced by the decay of zirconium. Hence, for the extrinsically enriched stars, for the chemically peculiar stars, we expect for them to have had enough time for the production of niobium through zirconium from the decay of zirconium. So we expect them to have a zirconium over niobium ratio of 1, while for the intrinsic stars or our genuine thermally pulsing AGB stars, they are freshly producing these S process elements, undergoing these third dredge-up constantly, and hence they haven't had yet enough time to produce niobium from zirconium. So you expect them to have a zirconium over niobium greater than 1. Basically, this is what you see in this diagram, where we could use the zirconium and niobium to distinguish the intrinsic stars from the extrinsic stars, the technetium-rich stars from the technetium-poor stars. And this is quite interesting because now we know that the zirconium and niobium abundances can be used as a complement to the technetium abundances, in addition to those technetium lines, to identify genuine AGB stars, genuine TP-AGB stars. Another interesting discovery from this diagram was these bintrinsic stars, which I have marked in this circle. So these bintrinsic stars, why are they bi? They are bi because they show technetium lines, so they are genuine. They show genuine intrinsic features through the technetium lines, but they also have a zirconium over niobium ratio of 1, which is a hint that these stars have also undergone a binary interaction previously with their former AGB companion. So these stars show features of intrinsic as well as extrinsic nature work, and hence we call them bintrinsic. So this actually, the discovery of these bintrinsic stars also reveals to us a new way of discovering AGB stars with companion, actually, which can be done now using the zirconium niobium analysis. So for the last part of my presentation, I will be moving to the technetium-rich M stars. Just to make it again clear to everyone that these M stars are young objects, the most young objects on the AGB, oxygen-rich stars. So basically, we do not expect them, and we do not think of them of having yet dredged up any S-process material or carbon or so on. However, there have been detections of technetium line in some M-type stars, and this is quite intriguing. So to investigate it, we collected some high-resolution spectra for some M stars from this Utentheller's sample to really check these technetium lines and to also further perform a spectroscopic investigation. So here I'm comparing the two technetium lines of 3 M stars in green with a spectra of technetium-rich S star as well as technetium-poor S star. And you quite see that the resemblance of these technetium features with the one of the technetium-rich S star is pretty clear, and this star is unambiguously technetium-rich. So definitely the technetium-rich M stars do exist, of course. So now we want to understand really how they produce technetium and what are their other parameters and so on. So to derive their stellar parameters, we basically obtained the first initial estimate on these parameters using the color diagram or using these J-K, V-K photometric indices. And then we confirmed these initial estimates of parameters, of these stellar parameters, by performing a spectroscopic investigation on a high resolution spectra of these stars, using a similar method like that of also the S stars, but this time for the appropriate compatible M stars model for these stars. And then at the moment, we have obtained a final set of parameters of these stars. The spectroscopic investigation for the S-process abundances is still undergoing. But here I present to you an HR diagram using a Gaia EDR3 of these S and M stars, the technetium-rich M stars and the S stars as well. What we see actually from the location of the technetium-rich M stars is that they are located beyond the predicted onset of the third dredge-up. So well and good. Again, it's consistent that they have technetium because they are really lying in this AGB zone in the HR diagram. But the question what remains is that they are at the same location as the S stars. So if they are at the same location in the HR diagram as the S stars, why do they show technetium? They do not show zirconium oxide yet. What is the real difference between these M stars and S stars? Why? Because if they would show the zirconium oxide bands, they would be classified as S stars and not as M stars. So the underlying question, yeah, sure, thanks. So the underlying question is, what is the difference between the S-process profile of these M stars and S stars? Another important takeaway message from this HR diagram would be that an HR diagram is really not sufficient for us to disentangle really the nucleosynthesis of these diverse group of AGB stars. So we really cannot do that just by an HR diagram. And our investigation on the S-process abundances of these technetium-rich M stars is still ongoing. I leave you here with the summary of my talk, and if you're too bored to read the summary, then you can check an artist impression of my summary, which is me trying to understand these M and S stars using Gaia. Thank you.
Thanks, Shreeya, for a very nice talk.
Thank you.
So we have time for a couple of questions. If I see that we have one question already. So thank you. Can go ahead and ask your question.
Thank you. Interesting talk.
Thank you.
Could you explain model A and H spectra on slide 3 a bit more?
Yeah, sure.
Which stellar atmosphere tables and atomic line lists and or code do you use to produce model A and H spectra?
So there's, I will go back to model A and model H. So the model atmospheres which I have used here is Mach's model atmospheres for S stars, because now they have recently released a special Mach's models for S-type stars. So which goes through a huge grid of these different parameters, as I mentioned here, which are really important for these S stars. The line lists which I have used, the atomic line list is the Jeste line list basically, which I have used, and then the different molecular line lists, including also TIO and ZRO and all these molecules as well. Now in our paper, actually, in the paper which I mentioned, which has been on arXiv last week, you can find a golden line list, an observational line list basically of these S process lines, which we have found with the high resolution spectra. Now to describe you a bit model A and model H, so the difference between these two models is that they have a completely different set of parameters, as you can see here. And they were derived using, these models were synthesized using turbo spectrum.
Thank you very much. I checked the paper.
You. Yeah, thank you.
Okay, so Sofia Hamstead also had a question, but I think she changed her mind. But I
okay.
raised my hand for Stefan, that he cannot raise his hand. So Stefan, you can go ahead and ask your question.
Yeah. Hi, Shreeya.
So
Thanks for
this is
thank you for the nice talk.
Yeah. Okay. Yes, I cannot see you, so I don't know.
Yes. So okay. Nice to see that you follow up on some of my work.
Yes.
Question I have is, so these stars are quite strongly variable. They are Mira stars.
Yes.
So how do you think can you take into account the variability in determining the abundances? I guess it would be tricky.
Yes, indeed, it is very tricky, and which is what I am kind of struggling / suffering at the moment, the high variability. So what I have tried to do is, from your sample, I have tried to use, firstly start with the stars with the lowest variability basically, and with the best signal to noise so far we have. So I'm trying to use these stars, I'm starting with these stars with the lowest variability, and so far, yeah, I've been able to constrain the parameters quite well, but the abundances still remain a challenge because of the high molecular veiling. So this is something I'm still struggling with.
Okay. Good luck.
Yeah, thank you. I will keep you. I will let you know. I'll keep you up to date about it.
Yeah. Thank you. Thank you.
Thank you.
Okay, we have one last question from Patricia. Go ahead.
Yeah, sure.
I'm just worried about using Gaia distances for these very, very red variable stars. Isn't that a problem?
Indeed, no, you're right. Indeed, it is. For many of our S stars, we actually realized a big difference between DR2 and EDR3, and which led, of course, further to a difference in the parameters, or which had some effects on the parameters which were used also in the abundance analysis. So indeed, for some stars, there has been this impact, because Gaia has not does not use these red sources for calibration, so they are not very well calibrated, and there is an impact from that. But yeah, we have to start with something. We cannot be waiting for the DR4 for things. So I have every time in a new study, we try to update the parallax and also the study hence. So from my previous studies with DR2, we have updated now to EDR3 and notified if any differences. Yeah.
You need to be very careful with those distances, because it isn't just the colors, it's also the movements of the photocenters.
Yes,
so the distances and the errors are unreliable at this stage.
Indeed, it is. I agree with you. It is. But we've tried to evaluate as much as we could how that also extends to how that would affect our results in terms of the parameters and also abundances.
Okay, so you guys can continue the discussion maybe on Slack afterwards, because now we have to move on. Thanks again, Shreeya, for
Thank you.
your talk.
Thank you so much.
So now we continue with Borbála.
Yep.
Sorry if I mispronounce your name.
No, it's perfect.
Cseh. Probing the slow neutron capture process in HB stars using barium stars abundances. So yeah, I see that you have already shared your screen, so go ahead.
Yeah, thank you very much. First of all, I would like to thank the organizers for giving me the opportunity to talk about this work here. I am Borbála Cseh from Concoli Observatory. And yeah, so first of all, I would like to give an overview. I will first introduce the barium stars, and then I will talk about the comparison of a large sample of barium stars and with models, and also take individual barium star abundances and compare that with different AGB models. And then I will summarize and give some of our future plans. So what are these barium stars? These stars are GK giants and dwarf stars with metallicity over around -1, and they show a very strong spectral features of carbon molecular bands and the elements of the slow neutron capture process, which elements were synthesized inside the AGB stars. So this raises the question of the origin of this overabundance. Are these barium stars intrinsic? So are these AGB stars or extrinsic? So they have the overabundance from a pollution of a former AGB companion. And yeah, it's not a surprise that these barium stars are not intrinsic. They show, as you have seen in the previous talk, that these extrinsic stars show lower luminosities compared to the AGBs. And the barium stars also show radial velocity variation and UV excess, which points to the binary nature of these stars, and that they have a white dwarf companion, which was previously an AGB star. And during the AGB phase, they gained mass from the AGB star, and that's what we can observe now. So this is the reason why we can use barium stars to test the AGB S-process nucleosynthesis. So the type of this mass transfer is still under debate. It can be stellar wind, Roche-Lobe overflow, or some kind of mixture of these. But I will now not talk about this. But yeah, so a little bit about the S-process. It happens during the thermally pulsating AGB phase, and it causes, in the abundances, it causes peaks at strontium, barium, and lead. And it arises the question how to measure the efficiency of the S-process, how to use these elements. Usually in the literature, it is used as the ratio of the heavy, so the second peak, and the light, so the first peak S-process elements, which is called HS over LS. And with this ratio, we can eliminate any of the dilution effects which can happen in the atmosphere of a giant barium star, if the barium star is a giant and not a dwarf. But which elements do you use when we compare these elements? So what is S here, S elements? What are the HS and LS elements? It depends on the study. But usually LS is the strontium, yttrium, and zirconium, and HS is barium, lanthanum, cerium, and neodymium. So in this study, we used the sample stars from the De Castro 2016 sample, which consists of 182 giants, which are certain and candidate stars. The spectra were taken with high resolution, with a high resolution spectrograph of Pharos, with the resolution of 48,000. And the spectra show wide range in effective temperature, in mass and metallicity, as we will see. And they considered barium star if the S over iron is over or equal to 0.25, where S equals to lanthanum, cerium, neodymium, yttrium, and zirconium. And based on this criteria, 13 stars were rejected from this sample. So at the end, we have 169 barium stars, homogeneous sample. So this is the largest sample in the literature, which is homogeneous. And in this study, we started, instead of using an average ages and an average ages over LS ratio and estimated errors, we used separate elemental ratios, and we also calculated the error bars for each of these ratios. And we compared these stars, these results of from the spectra with different AGB models. So we used the same criteria for these AGB models with the same elements counted as S. And S over iron has to be over 0.25 to compare with a model. And we used models without rotation, since it looks like the rotation is not causing a large effect in AGB stars when we compare to these observations. And a wide range of metallicity masses and different C13 packet sizes are involved in these models. We used the most largest set of models from Fruity and Monash, which have many different metallicities and masses. And as you will see, we have also some new-grade models in this range of metallicity of the barium star sample. So if we compare the whole sample to the models, you can see in this plot on the x-axis the metallicity, iron over age, and on the y-axis you have 4 different ratios for cerium over yttrium, cerium over zirconium, neodymium over yttrium, and neodymium over zirconium. And you can see the different models. For Fruity, it's the dashed line. We have 2 new-grade models marked as triangles, and 3 different Monash models. So the Fruity and Monash models are for 1.5, 3, and 4 solar mass, and the new-grade model is a 3 solar mass model. And as you can see on this plot, all of these models agree with the observations. The trend is the same. So if we move to larger metallicities, the different ratios of the AGES and LS type elements are lower, as it is seen also in the models. 28 stars from this large sample were included in the paper from Ellen Jorison and collaborators to calculate the orbits and the masses of the different barium stars, and also estimate initial AGB masses. You can see in this plot on the right, in red, these 28 stars. It is the cerium over yttrium ratio in this sample, in this case. And you can see that the 28 stars are all around in metallicity and in the cerium over yttrium ratio of the large sample of the 169 stars. To compare the individual stars with the models, new elemental abundances were also calculated for rubidium, strontium, niobium, molybdenum, ruthenium, samarium, and europium, and also new lanthanum values with improved atomic data, and also the hyperfine structure included are presented for these stars. And you can find the details in these 2 papers by Michel Rollis. One is to be submitted very soon. So when we compare these stars, as I said, these sample stars are all giants, so they have a huge convective envelope. So when the AGB mass carries to the secondary, it is mixed and diluted with the envelope of the barium star, the current barium star. So when we do the model comparison, we have to apply dilution. And we calculated dilution factor delta to match the cerium over iron ratio of these observations. And the models that I will show, they have very different C13 packets where the neutrons are released to produce the higher elements heavier than the iron. And we have taken the models in the metallicity range within the error bar of each star. So here is a first example of one of the barium stars. Here you can see that many models with different colors. It's a solid line for the Fruity models and dashed line for the Monash models. And also you can see the estimated mass of the barium star and the initial AGB mass from the Jorison paper, and the metallicity. So as you can see, the models have different metallicities. These are all within the range of the barium star's metallicity. And you can also see the dilution factors of the models. So if delta is closer to 1, it means that more mass is necessary from the AGB star to match the cerium over iron of the barium star. And in the top plot, you can see the elements as stars, these yellow stars, and with the error bars. And this is what we have. We plot all the elements and all these models what you can see down. So here in parentheses, you can see the different C13 packet sizes. So the fruity, let's say normal packet sizes are not shown because that's the standard. They have also to extend it, so a bit larger packet. And for the Monash models, the larger numbers mean larger packet sizes. So in this plot, you can see that the models which are at rubidium, they are deviating a lot for the higher masses. And in this case, we can see that the rubidium is mostly closer, and within the error bar of the rubidium is closer to the 2.5, maybe 3 solar mass region of AGB masses, which is in agreement with the AGB mass derived by Jorison and collaborators. So this, in this case, we are in a very good agreement for the whole abundance pattern of the S-process elements. The next star is shows the same models from Fruity and Monash, but in this case, the agreement is not really good. So it's a pretty low AGB mass. And with this model, we cannot fit the first S-process peak. So we are again normalizing the models to the cerium over iron. And in this case, you can see that the delta values are really low. So it's a little amount of mass that is necessary to match the cerium coming from the AGB to match the cerium over iron of the observed star. But I have to mention also that the metallicity of this model is lower than the metallicity of the barium star. So this might cause also some discrepancies in the comparison. But what is happening here? So as we have seen, these models from the Fruity and Monash models cannot reproduce this first peak. Maybe they need a different neutron density. But Shreeya showed in an earlier paper that they were able to match with star-evolved models low mass S-type stars or AGB stars. So this might be another example of this. So the polluter AGB might be another example of these low mass AGBs. And for summarizing, out of the 28 stars, we had a good match with 25 stars, and only 3 of these show this higher first S-process peak, and all of these 3 stars have lower mass, AGBs lower than 2 solar mass. So a summary of my talk. So as I have shown, the barium stars are polluted by AGB stars. So all of these AGB stars are low mass AGBs, so they are below 4 solar mass, which means that the C13 is the main neutron source. We have found good match with 25 stars with the models, and the 3 stars show higher first peak in the S-process peak. And we can use rubidium to estimate the mass of these stars to constrain. If we have rubidium abundances, more stars will come with the same abundance pattern for the whole sample of the Castro sample that I showed at the beginning. And we are also working on the machine learning methods to derive the masses, not going through all the stars separately and manually. And we are also planning to include other sets of models to check the different parameters and processes that can happen in AGB stars and to find the best fit to each of the individual barium stars. And thank you for your attention.
Great, thanks Borbála for a very nice talk. We have time for a few questions. So if you want to ask a question, please raise your hand using the reactions button. Maybe I can start off with my question. So you showed this dilution parameter, and what is exactly the meaning of that? Is that if it is 1, it means that the composition is exactly the same as the accreted gas?
Yes.
And so how much mass do you expect this accreted mass to be diluted over? Would that imply very high? Because I saw that some numbers approached 1 for some sources. Would that imply very high amounts of accreted mass, or is that something that is expected?
Yes, so we are not waiting that much. So yes, as I said, the mass transfer mechanism is still under debate, but we are not waiting that we can reach as much as delta equals to 0.9 or something like that. We have set a limit at delta 0.9, but yeah, that's pretty much, and these are unreliable. We don't expect to see something like this. So maybe in this case, maybe it is close to 0.3. That might be something which we can believe it happens.
Okay, so yeah, but do you know how much accreted mass that would correspond to roughly?
We haven't calculated it yet, but we are planning to do it.
Okay. There's also a question here in the chat from Meredith Joyce. Thanks for the talk. Is it possible to change the underlying reaction rates or nuclear network in any of the codes you used? And if not, is it possible that the reaction network and or rates are responsible for poor agreement? More specifically, if uncertainties in those rates were taken into account, could they resolve the disagreement for HD 13, whatever the source name is? Yeah, that one.
Yeah, I am not an expert on the models, but yeah, definitely we have also some uncertainty coming from the nuclear reactions. Yeah, in this case, we also plan to run other models for closer to the metallicity of the star to check if that makes any difference. But I don't think that we can go that high up with these models.
Okay. So if there are any other questions, please write in the chat or raise your hand. Okay, so thanks again, Borbála, and thanks again for all the speakers of this session. Had very interesting talks and discussions.